What about now? I think.
Yeah, I should hear my own.
No, I think the idea is that. Okay. I see there's still an echo.
Oh,
You need to, you know what? No, I don't want to use your microphone because I think it's probably not going to pick up. When you join the Zoom meeting, it asks you to join with audio, so if you can just disconnect your audio entirely. We're about to start.
okay. I'm just
All right,
connecting
we're
it.
good?
Yeah.
Is the sound okay? Okay. Okay, very good.
Yeah.
Okay, so it's my pleasure to welcome Vikram. I mean Vikram from University of Maryland. He has done several exciting. He's made several exciting new countries. He's a graduate student in his 6th year looking for a postdoc. And he's made several contributions to the theory of quantum chaos. I've heard about it from Victor Galitsky, and I'm glad to see you in person. Let me see. There's two little lights.
I think my iPad is still like.
Your what?
My iPad still has like some sound, so let me try to.
I see. I mean, if you want to transfer the talk and give it from the desktop, that's fine.
Let me just try this one now.
For the people in the audience, coffee is on its way. There's hot tea and there's their name tag, but no. But let's just start the talk. I'm just kidding. Keep the name. Okay, ready to start?
It's still picking up a little bit, but hopefully that won't do much.
You can stand here. Maybe
Yep.
that will be less of a.
Yep.
Let's get some physics in the way. Okay. All right, I'm not gonna dim the lights. It's good enough. Okay, let's start.
I'm Amit Vikram. I'm a graduate student at UND. I've been working on different aspects of quantum chaos. So in today's talk, well, it's called quantum ergodicity beyond random matrices. And as a kind of overview, the goal here is something like this. In quantum statistical mechanics, what we normally have is we take a system, we compare it with random matrices, and at this point, assume that it implies something about the validity of quantum statistical mechanics. There are good reasons for doing this, which is that we see in several systems that thermalization in the sense of statistical mechanics seems to be connected to random matrices. But we don't really have a first principles understanding of that in general, and this is like an attempt to get to that in some sense. So yes, based on this recent work that was published in Physical Review Research, I also like mention the archive version because it's single coordinate case.
So state it again. The problem is what? Why the Bose-Einstein distribution is correct?
Indirectly, so more like a microcanonical distribution, but not just that specifically. It's more about how the different things that work together to give you classical statistical mechanics emerge from quantum mechanics, including the microcanonical ensemble, but not directly that. And I'll get to the specifics shortly.
So don't give a precise problem.
So the precise problem, if you want me to state it, is there a quantum version of ergodicity that we can connect to eigenvalues, for instance? Or from another sense, what does the ramp in the spectral form factor really tell you about quantum dynamics?
What is this second last one?
So, for instance, something like the ramp in the spectral form factor, like which is considered a measure of random matrix behavior. What does it actually tell you about quantum dynamics? So that's more like a specific problem, but I'm kind of approaching it from a more general angle. And yeah, I won't actually be talking about spectral form factors here, so it's just more about eigenvalue statistics. How does that connect to quantum dynamics? Okay, so to motivate why we are doing something like that, let's just review what happens in classical thermalization and why it's difficult to extend to quantum. In classical statistical mechanics, we have the microcanonical ensemble, which is essentially the assumption that we have equal a priori probabilities over the phase space. So in this kind of schematic of a phase space, what happens is we have an equal distribution of points that goes everywhere, and we assume that we can use this description to derive other things like the thermal state. And the classic question has always been, when you have something like a Hamiltonian system that just follows precisely defined trajectories in phase space, why would that be well described by an ensemble of points which is just spread all over the phase space? And that's kind of the problem of thermalization. Classically, the kind of historical solution to this is Boltzmann's ergodic hypothesis, which states essentially that when you fully explore the phase space, then you end up getting something like the microcanonical ensemble as follows. So let's say that we have a trajectory and phase space. When we average the trajectory over time, if it's a finite amount of time, and we kind of consider smooth observables that can't see the precise trajectory, then we end up getting something that's just like a distribution of points. And visually, what I've done here is I've just taken this trajectory and removed the line. So you just see the arrowheads, and they seem like very microcanonical, very equally distributed. So that's a schematic representation. To make this more formal, it's conventional to take an infinite time average, in which case all observables are kind of described by this microcanonical ensemble. You want like the expectation value of the observable averaged over time, that's given by the microcanonical ensemble. So on time averaging, we get statistical mechanics from both the ergodic hypothesis. It is also important to emphasize that this is really just an idealization. So in a mathematical sense, ergodicity is necessary and sufficient if you want the microcanonical ensemble to describe all time averaged observables and almost all initial states. So we just want to generate trajectory to explore the phase space. In practice, if you have an individual observable that can thermalize without ergodicity, as long as you're just concerned about the one observable. So what could happen in practice is the kind of observables you can access in the system, they all end up, let's say, having the thermal value for the expectation values through some coincidence. And you don't really need ergodicity in that case, but for this much stronger version of all observables thermalizing, you do. So what we're really studying here is an idealization, but hopefully an idealization is well, where we can begin to make like progress towards understanding. So ergodicity is about time average thermalization. And there are other notions of randomness in exploring the phase space that also begin to describe how fast the system approaches some kind of microcanonical description. One of them is mixing, which again in a schematic just talks about diverging trajectories. And then there is k-mixing or chaos, which is like the most well-known of these properties in some sense, that talks about exponentially diverging trajectories. And in addition to trajectories, of course, different notions of mixing need ergodicity to begin with. And when you have these different properties, what you can do is formally mathematically classify dynamical systems into what's called the ergodic hierarchy, where at the most fundamental level, you have this property of ergodicity that reaches a microcanonical ensemble. And then you have different properties that describe how fast you get in a microcanonical ensemble. And the overall statement here is there is a very precise understanding in ergodic theory of all these properties and how they connect to different systems and so on. It's of course hard to prove these for most systems, but given that they exist, like they're pretty rigorous properties. One important aspect of these properties to emphasize here is observable independence. These are actually properties of the system itself rather than any specific observable. And what that means is all observables should either be ergodic or show this mixing property and so on without exceptions.
Can you say more about this figure? What's lambda?
Lambda is the Lyapunov exponent, so that's like a measure of chaos. So when you want this exponential divergence of trajectories, which is what like lambda measures, that corresponds to this Kolmogorov mixing level, which is like a very specific type of ergodicity. That's a special case of ergodic systems. And then there's like the Bernoulli level that's again chaos, but it's something like pure chaos. You don't have a component that's non-chaotic within the system is a very like simplified way of putting it. One way to intuitively consider all this is ergodicity is about exploring the phase space.
Can I just clarify that? So Kolmogorov would be where you have few invariant tori left, and Bernoulli is where there's nothing.
It's not about invariant tori, so it's more about like
What's the difference between the Kolmogorov?
okay, so there is something like you can take a kind of chaotic system and factorize it into a fully random system and a non-chaotic system that has like well that does not have any randomness from one point, so it can be like strongly mixing but not chaotic. And the Bernoulli system is that fully random system. One example of that would be something like a coin twist.
K is that all factors are it doesn't have factor with zero entry.
So if you factorize something with like another way of talking about this is there's something called the Kolmogorov-Sinai entropy. And when you have a non-zero Kolmogorov-Sinai entropy, which is like the sum of the Lyapunov exponents in some sense, that's a case system. But just a question actually to your comment, when you factorize a case system into something that has a non-zero entropy, or let's say the full entropy of the case system, then wouldn't the leftover, if that's also a factor, like have zero entropy, or is there like nothing left over?
There is nothing yet.
Okay. So these are essentially like chaotic systems. Bernoulli systems are like purely random systems where each successive step is not correlated with the previous step. Case systems, there can be some correlations that kind of disappear in the long time limit. That's another way of looking at it. So the overall point here is just that there are like several different precise classifications in ergodic theory for these systems, which in some sense describe different levels of emergence of statistical mechanics. And these are all properties of systems, not of observables, so they're like very strong criteria, at least in an idealized viewpoint.
Do you know where like the pendulum would be in this hierarchy? Since we were talking about it yesterday.
No, it's
So the pendulum is
outside.
It's not-
Not even the goal. So the whatever, for example, the portion was in what we
Yeah.
know. And the body is the rational rotation.
I see.
And there's also like modular multiplication, for instance, with Bernoulli. Something like chaotic billiards, if you have something like stadium billiards, Sinai billiards, like billiards with like curved boundaries, then that's a case system. So that's like locally you have some correlation between trajectories and what happens next, but you wait a long enough time, things become completely uncorrelated. Mixing, one example would be, let's say, triangle billiards, for instance. Triangle billiards are not chaotic, you don't have exponential divergence of trajectories, but still eventually trajectories kind of spread out and become random over the phase space.
I don't think there is any example of a triangle billiard that is known to be mixed.
Triangle billiards are mixed. Irrational triangle billiards. So when you have the angles as irrational angles,
Isn't it rational? I'm not sure it's not.
they are mixing from what I mean.
So the square.
The square would not be a good. The square would not be a good.
No, we understand. You're talking about irrational triangles.
Yeah.
We know is that they're all that generically they are weak mixing.
Yeah.
But I'm not sure there is any
So
example.
you're talking about weak mixing versus strong mixing.
Weak mixing, yeah.
Yeah, okay. So irrational triangle billiards are mixing in the sense of one of these. Precisely about whether it's strong mixing or weak mixing, I haven't. Yeah, but polygonal billiards in general are not Kolmogorov, they're at best mixing. That's
Where do real systems lie on your picture?
Huh?
Like systems in the real world?
systems in the real world probably lie outside because you usually have like conserved quantities that even prevent ergodicity. But once you get to a subspace of that conserved subspace where like you have fixed values of all conserved quantities, you will definitely have ergodicity. And this is like a series of subsets. So, for instance, Bernoulli systems are also ergodic. These are contained within each other. And real systems, so again, if you have point tosses, they're like Bernoulli or some kind of Béliard's word.
Point tosses aren't actually, but me.
Why aren't?
Look, if you take the pendulum, yeah, the phase space decomposes into invariant circuit, on which the dynamic is usually a rotation. It's like a rotation. And now one of the biggest questions in dynamics, it's mathematics, physics related to dynamics, is if you perturb the pendulum map, the time one map of the pendulum, does there appear a positive measure for the ergodic component that is safer than that? This is not known. That's answering the question, where do physical systems stand? We don't.
So in this case, what we're saying yesterday, the excited pendulum, the force pendulum, they have portion. And now the question is, maybe this set where you have this kind of hyperbolicity could have positive recognition. It's unknown.
But in comparison, you take the billiard, semi billiard with gas particles that heat and elastic collisions. This is very good. That's very good. And the pendulum is outside, it's at most ergodic on its ergodic component. We don't know if there is anything Bernoulli hiding. There is this horseshoes, but they have zero measure. Okay. And gas billiard, they are the
Strongly mixing the holocycle forward from the
exactly zero.
and they are induced by.
Can I just ask, this is still a review portion of your talk?
Yeah.
I actually want to hear final results.
Yeah.
I understand.
Thank you.
Okay.
No, please,
Can we
come on.
continue?
We're organizing too. We would like to hear more about what you.
Well, should the
Okay.
organizers vote on whether to continue?
No, come on, but don't shut up with the other people. We would like also to make questions, but yes, keep going.
Because there's gonna be a long discussion.
Okay.
But for one, I also read final interesting that pendulums might have these like Bernoulli things and yeah, so I mean it was also like interesting. Classically we have a kind of precise idealized understanding of how dynamics leads to statistical mechanics. Quantum mechanically, there are some issues, which is a classical understanding. Well, at the simplest level, a classical understanding has a phase space, and it entails exploring the phase space in terms of a trajectory. In quantum mechanics, there is no precise phase space, and there are no precise trajectories that play a fundamental role. They're all like emergent in the classical domain. So we need kind of different notions to actually talk about quantum versions of these. On the other hand, what we do have quantum mechanically is this microcanonical ensemble. That is relatively simple to define and use, which is we just have a density operator that's like an equal probability distribution over energy eigenstates in some window. And so let's say there are like the energy eigenstates within that window. These are just projectors onto the energy eigenstates added up to each other. This is an equal distribution over all these energy eigenstates, and by extension, it's an equal distribution over any basis in the subspace spanned by these eigenstates. So this is like a quantum microcanonical ensemble, and well, it seems to work, at least in idealizations. But the problem is we don't really understand why we can use it, which means given a system, how do we show that this kind of ensemble really works? And this is like a broad problem for justifying quantum statistical mechanics. And what we do have, instead of directly justifying anything like that, is a procedure by which we look at the energy eigenvalues and the energy eigenstates, consider how they are distributed, and then say that if they're distributed a certain way, then we are justified in using this. But again, the justification is more empirical.
So here's the question, didn't ETH solve the problem?
I will get to ETH, but so to kind of cover that a little bit before we get there. In fact, it's going to show up in 2 slides. What ETH states is if matrix elements have a certain form, then you have thermalization. Which is this part, you're looking at eigenstate statistics to give you the thermalization. Go.
It's fine, if you get to reduce like.
Okay. I'll just get this.
So again,
So we'll be looking at finite dimensional quantum systems. So we consider a time independent quantum system, which means we have a unitary that can be thought of as being generated by a Hamiltonian. We're not going to pay careful attention to the difference between continuous and discrete time, but in principle, they can be either. Time can be a real number or just the integers. And we have a d-dimensional Hilbert space. And in principle, the energy eigenvalues and eigenstates should know about every property of the unitary time evolution operator, because you can reconstruct its action on any pairs of states from the energy eigenvalues and eigenstates. The issue is, of course, that diagonalizing matrix is hard and obviously far from being intuitive. So even though all these properties should be encoded in these eigenvalues and eigenstates, we don't really understand the full extent of how that happens. And what we do instead are getting to two empirical principles, which is comparing to the properties of random matrices. The first of these is that the microcanonical behavior of observables corresponds to random states in the Hilbert space. This was initially observed by von Neumann and then kind of obtained by others again in the early 2000s. And I think one convenient modern name for it is canonical typicality. What this really states is when you pick a random state in the Hilbert space. So here is just an example to illustrate how this happens. Let's say we have 11 qubit system. Each system has like 2 degrees of freedom, so a 2-dimensional Hilbert space. We tensor them together, we get a 2048-dimensional Hilbert space. And let's say we consider 3 qubits amongst the system and kind of just look at the different configurations of the 3 qubits, combining all the rest. Then if we have a random state in the Hilbert space, over the basis states of the Hilbert space, it kind of fluctuates randomly with some kind of average value. But if we aggregate them over these states of a smaller set of qubits, in this case, we have 3 qubits, so that's 8 states. We get something that's like rather close to being uniform. So the fluctuations around the average value are small. And in practice, what will happen is as we increase the number of qubits to infinity, these fluctuations will essentially disappear and we'll get a smooth microcanonical behavior. So this is one principle, which is that observables and small subsystems, they tend to show microcanonical behavior in a random state.
So second, what's the blue line?
So the blue line is like the probabilities represented by the random state aggregated within the basis states of these qubits. So essentially like tracing over the rest of the system.
So you take the state psi, you trace out
Yeah.
8 qubits, you get
Yeah.
the matrix supercube. That's
Yeah, it's essentially just summing over the diagonal elements. So you take the probabilities for each of the states that correspond to, let's say, the 000 state.
So why are you using the basis states?
Because we're looking at the behavior of basis observables. Let's say we want to understand how projectors on these observables dominate.
And psi is a random state?
Yeah, like a hard random state, which is like completely randomly chosen in the Hilbert space.
Okay, so second, why are basis states special?
Because ultimately we want to make an observation, so there's just a choice of states. Obviously, given that there's a random state, this can be like any state in the Hilbert space, relative to which this psi state is random. And in practice, for an illustration, I'm just calling these qubit basis states. No explicit qubits were used in making this plot. There's just like a bunch of random basis states relative to which the state is random. And the qubits are more like a physical crutch to like motivate that.
Okay, so can I just repeat what you said?
Yeah.
And you tell me if I got it right. So the idea is that there are some states beside which are chosen to be hard random, and they're cartoons of what an eigenstate would be.
Yeah.
Roughly speaking, because
Yeah,
the idea is
you
that
can
eigenstate is structureless. So that's your state, that's your probability distribution. But then what you look at, the reason you choose basis states for the subsystem of 3 qubits is to say that these are the physical observables that I can measure. And you want to say that suppose, because in classical StatNet, there's probability distribution for nothing else, you don't have wave functions. Right, so the idea is that if I looked at it through that prism, if I just wanted to look at the probability distribution,
Right.
what probability distribution do I see?
And it's
A flat
microcanonical.
distribution, yeah.
Yeah.
Okay.
So this is one way in which microcanonical probability distributions emerge. And so getting to eigenstate thermalization hypothesis, one refinement of this principle is that microcanonical behavior would emerge from random eigenstates. And why would that be the case? Well, in classical ergodicity, we consider time averages. And if we time average over a density matrix composed of some initial state psi as it evolves in time, then all terms that involve off-diagonal combinations of eigenstates, something like the contribution from En to this and En to this, they kind of cancel out because of the time averaging, because it's just a case. And what we are left with is just each individual eigenstate. So the kind of principle here is time averages are determined by individual eigenstates, and if they look random in the same sense as above, then that kind of implies thermalization. And this is a simplified cartoon of the eigenstate thermalization hypothesis. There is like a more detailed matrix element structure. But what it's essentially saying is that eigenstates, if eigenstates look random, then you get microcanonical behavior. But it's not a complete solution because there are some conceptual issues here, which is in every system, ETH is satisfied and violated by essentially the same number of operators. So for instance, if you take the energy eigenstates themselves, they do not have a microcanonical distribution given ETH, because no matter what the structure of the energy eigenstates is on some other basis, you start with a single energy eigenstate, its distribution is peaked at itself, and no other eigenstate. So energy eigenstates never take the microcanonical value. And more generally, we can construct like simple modifications of energy eigenstates, which are also like distributed not uniformly. And what this really means is we don't really have an understanding of which bases or operators would actually like satisfy ETH. Or what that means is which bases are the ones in which the energy eigenstates look random. Of course, we can write them down. We can just write down a basis and say that the energy eigenstates are random in this by, let's say, writing the matrix elements of an operator in the energy eigenbasis. But the question is, how do we connect that to some kind of physical dynamics where, let's say, we know the Hamiltonian or something like that? And the other question is, of course, when random eigenstates are really necessary.
So basically everything goes well. You have this property that they are going to behave randomly.
Yeah, so the assumption is if they behave randomly, then the corresponding observable term.
You are right. Okay. But this is hypothesis. Nobody know really it makes sense, or they are something where you can assume this hypothesis.
You can assume this hypothesis and show that things normalize.
Okay, but you say, for instance, you have a classical Hamiltonian in some way you quantize.
Yeah.
It's well known which are the properties of the classical Hamiltonian in the way that when you quantize, you will have the hypothesis.
Specifically random behavior, but for certain kinds of systems, like let's say billiard systems, or I think more generally it's some kind of particles on Riemannian manifolds. This is essentially a version of Schnirelmann's theorem, which states that when you have an ergodic classical system and you consider certain kinds of observables, then they need to have essentially the thermal expectation value and energy eigenstates. So it's like classical ergodicity implies thermalization and individual eigenstates.
So if you pick up the slide about the previous one where you classify all the different type of ergodicity.
Yeah. This.
Yes. So let's assume that you have a Hamiltonian for each one of this those systems.
Right.
And then you have the quantum version of each of them.
Right.
In which one can you say that the random hypothesis holds?
I don't think there's a clear understanding of that.
Okay.
There are pointers that it could be one of these, weakly mixing or strongly mixing, but there's no clear understanding of that.
But Bernoulli, for Bernoulli,
again, there is no clear understanding of that. So quantization is in some sense a strange business because there is no like unique way to quantize a classical system.
So it would depend on the way that you.
Yeah, it would depend on the way you quantize. We know examples of Bernoulli systems that do not satisfy eigenstate thermalization if you quantize them a certain.
What's the example?
Modular multiplication by a given number in some unit interval. So if that is quantized like on some subset of the instead of taking a unit interval, if you take like a set of integers and you look at modular multiplication, then they have like separate periodic orbitals. So they're not even recorded.
How are you gonna find ETH if there's just
ETH is just about like the structure of eigenstates, so it does not depend on whether it's like one particle or many particles in the sense I'm referring to it here.
But so ETH it's assumed that you have many particles. Otherwise,
That is for the specific matrix element expression where you have that entropy which depends on like the number of particles. The sense I'm referring to here is the sense of random eigenstates, and you can have random eigenstates in a single particle, so like you don't need a nice particle. And in fact, mathematically, the most rigorous counterpart to ETH is a single particle continuum system.
actually, can you go back to your slide? I didn't understand what the problem is with ETH.
Single particle billiards have this property, random states.
They don't show random eigenstates. There's no known way to prove that the eigenstates are random. What they show is that observables have the microcanonical expectation value in individual energy eigenstates.
Say it again, they don't have random eigenstate, but.
We can't prove that they have random eigenstates.
Okay. They don't.
Numerically, they seem to have random eigenstates. But observables get to the microcanonical expectation value in individual eigenstates. That's what can be proven.
Mm.
And that's called Schnellmann's theorem. So it's a pretty-
For in Iberia, let's say,
yeah, yeah.
for the real okay.
Yeah, so the issue with ETH is it's kind of stating that if you have random eigenstates, things thermalize, but we don't really understand the mechanism for random eigenstates more or less. And there are clearly observables for which you will definitely not have random eigenstates. So it's more like addressing the question of thermalization with a hypothesis that is very useful in applying to problems. There's also the question of what the origin of this hypothesis is.
So what do you mean by random eigenstate?
Random eigenstates meaning energy eigenstates. So these energy eigenstates, when they look random like this, more or less. And that was kind of the original motivation for ETH, which is when you have random when the energy eigenstates are random and like systems with a classical limit, that's called Berry's conjecture, energy eigenstate being random if you have a sufficient degree of chaos, then you can get the kind of matrix element that like Srednicki writes down.
And so, and the definition of ETH is exactly these conversions. No.
ETH, so this is like a simplification of it. There is a kind of matrix element expression. But one way to think about ETH is every energy eigenstate looks random in a given physical basis. Or almost every eigenstate does, like weak ETH and strong ETH. That's a simplification, but I think it's a good enough simplification for what we are like talking about.
But okay, the ETH just states that if you take an energy eigenstate from almost anything you measure, you won't be able to distinguish it from the thermal state.
That's one way of looking at it.
You take the problem Srednicki was solving is this. We always use the thermal state, but there's no justification. He says in quantum mechanics it's even easier. Just take any energy eigenstate, compute anything you like, you won't be able to tell the difference between that and the thermal state.
Okay.
Yeah, but then the question,
The small things.
yeah, the question there is really why can you do that? Why would an energy eigenstate look indistinguishable from a thermal state? So given your way of phrasing it, that is how I would phrase these questions. Why would the energy eigenstate look like a thermal
So is there an example where ETH is violated for a system that's not integrable?
state? Yeah, again, modular multiplication, like I mentioned earlier.
No, that doesn't count.
Why not?
This paper starts by saying it's specifically many degrees of freedom, otherwise we're not doing statistical mechanics.
So, can you go back to that previous equation? I mean, I feel like this is too kind of axiomatic and not really intuitive. I think the intuition for why an energy eigenstate would be thermal looking the way I understood it is because like when we teach thermodynamics, we write these subsystems. The observables that you're allowed to talk about are the safe ones are few body, like basically local
Yes.
observables. The eigenstate is the universe, right? Like I was told that one of the early objections to Sridniki's work was that look, the universe doesn't have a wave function. Objection. Anyway, the idea is that if you think in terms of subsystems, the eigenstate is a stationary thing, so it naively doesn't have any dynamics. But if you look at that formula, right, that formula actually looks at all of the fluctuations. You see the eigenstates emerge as a dynamical process of stuff sloshing back and forth between the subsystem and the environment.
So how do you say that it emerges?
You see the time dynamics?
Yeah,
So eigenstate is a stationary solution of the Schrodinger equation.
Yeah.
Once you give me an eigenstate, there's no dynamics actually. It's very unphysical. So I feel like eigenstates are mathematically sharp, people love them, but they're not physics.
okay,
They're kind of like, they're tools for the calculation.
and you say that if we.
What I'm saying is that this definition of how to think about as a quant, this is a quant, you have some wave function state at time zero, it's not an eigenstate, it's just rattling around. And so if you think about the way we discussed classic thermalization in books, so we say, okay, there's some subsystems, the dynamics that you want to produce thermal distribution, and the Fokker point or whatever, there are formal ways of deriving it this way, is that because the subsystems are connected, there's going to be some fluctuations back and forth, and you're going to dynamically explore the whole. So from the local point of view, you're going to dynamically explore. And I think writing things like that basically kind of like at least hand wavingly explains to you how when you look at eigenstates, you're actually looking at this dynamical process of letting things like on time average. But this is just this is how people rationalize, the eigenstate should look thermal. Like you want to think of blurred eigenstates with this sort of a time integral. But again, this is not a computation. This is just an intuition. At least that's my intuition.
To like more also directly address like Vladimir's comment. So the question we are trying to address is more like why does the system thermalize, and what ETH does is move that to the point of why does an eigenstate thermalize. But there's still the question of why it thermalizes. You've just moved it from an arbitrary state to an eigenstate. Or does that? I think that's
So sorry, but the question was that do we know examples of, the examples that people tend to cook up is where there's a weak link between the subsystems and you make that weak link very inefficient and maybe right, localized system, systems that exhibit any kind of localization break APT.
And about many body examples, I just remember that there was a paper last year by Aaron Harrow and Yichen Huang, which actually constructs a kind of very artificial, but many body system that exists, where you have thermalization, you don't have eigenstate thermalization in a certain regime. And it's like some very specific construction, but there is an example that is reasonably. But also like many body systems and single particle systems, the difference I guess becomes important when you're considering like the specifics of physical observables. As far as the Hilbert space is concerned, there's not like too much difference. These properties are like very similar in both kinds of systems. And we'll get to that in a much more specific way with the next property. So yeah, there's eigenstate thermalization. So it gives you the microcanonical ensemble, but we don't understand the justification for it to summarize. And then there's another empirical principle, and this will be the focus of this talk. And this empirical principle is that classical chaos, loosely defined in the sense I can't exactly point to a member of that hierarchy that was there a few slides ago and say that that is the level of chaos I'm talking about. But classical chaos, loosely defined, corresponds to eigenvalues that look like the eigenvalues of random matrices. Originally, this was motivated by quantizing classically chaotic systems like Sinai billiards or Konemovich billiards, numerically looking at the spectrum. And then you see that the spectrum within sufficiently small energy windows looks like that of a random matrix. There's like three kinds of random matrices. The distinction between them is not too important for this talk. They're just called like COE, COE, CSE. These are unitary matrices, or distributions of unitary matrices more precisely. And the eigenvalues of classically chaotic systems on quantization show patterns just like these random matrices. And in parallel, there is this other observation that when you have an integrable system with a lot of conserved quantities, you get what's called Poisson statistics, which essentially means the energy levels are like randomly distributed and you can't detect like any obvious correlations. And one thing I guess that will be useful to emphasize is what these kinds of statistics actually look like, because the kind of measures you can deal with analytically most easily are not very intuitive. So for reference, here is a regular spectrum. And since we're talking about unitaries, these all span like 0 to 2 pi, which are the eigenphases of a unitary. So the blue one is a regular spectrum that's just regularly spaced. And the one just below that is for random matrices, where you see that there are tiny fluctuations around a regularly spaced spectrum. And the last one is for a Poisson distribution, which is supposed to correspond to integrable systems, where the fluctuations are pretty large. Quantitatively, the spacing between different levels, that's like order 1 over d. And the size of fluctuations relative to that spacing, that's square root of log d for random matrices and square root of d for Poisson distribution.
And then the problem that you mentioned before about the quantization is what happened with the quantization very sensible to the way that you quantize.
Yeah.
This problem.
It exists here too.
It still exists here.
Yeah.
Okay.
So, which is why these are just observations, which is why like usually is kind of highlighted here. So the way we tend to do it, we usually find this to be the case. Yeah, it is like a very imprecise notion, which is kind of part of the motivation for this project. So yeah, when we have a classically chaotic system, the kinds of quantization that we are usually comfortable with give you random matrix eigenvalue statistics.
So you start with the, okay, that this is, because there are many assumptions, so. You assume you have a classical system.
Right.
You assume chaotic.
Yeah.
And then you say that you are going to replace this classical well-defined, whatever, by some Hamiltonian as a problem of random matrices. Because in general, it's not true, no? So.
No, you're not replacing the Hamiltonian with the random matrix.
What are you doing?
You're looking at the energy eigenvalues of the Hamiltonian of the quantum system. And then you're computing statistical measures of those energy eigenvalues.
Okay.
And you find that those agree with the statistical measures you get from random matrices. So it's not about the structure of the matrix, it's about the distribution of the eigenvalues.
Yeah, because in general, there are many examples of classical chaos that doesn't have any relation with the random matrix. They are not very random matrices.
Yeah. So for instance, these papers, we studied Sinai billiards and Borimovich billiards.
So Sinai billiard, this is the classical Sinai billiard. The matrices that you are multiplying, the eigenspace are more or less all aligned.
No, these
Yeah,
are
different
matrices.
There's no random matrix in the classical problem.
They are not random.
The random matrix is just like over here. And you get statistical like 2-point function from the random matrix. And then you compare it to what you get from the quantum system. And then
Okay, so it's not about the definition of classical chaos. What you say is you lose the distribution of eigenvalues.
Yeah.
Of the quantized system in whatever way you do it.
and just compare it to this other
Yes.
system.
And you compare that in principle totally unrelated to the classical one.
Yeah.
So the distribution of eigenvalues are going to be like the distribution of the random multiplication of edges.
Not multiplication of
Multiplication is
Like,
matrix.
what are random eigenvalues matrix?
like a matrix that is chosen according to a Haar ensemble, which is like, let's say you have the unitary group and you have the Haar measure on the unitary group, and you use that to choose a matrix, then the eigenvalue distribution you get will be the same as that of these classically chaotic systems. In most cases, in the forms of quantization that we are comfortable with, because again, there are several exceptions, which is in fact one of the unsatisfactory aspects. Of this. So that's why the word usually is kind of highlighted here. And this is far from a kind of statement that a mathematician would be comfortable making. So there's really like a physical observation in some sense.
And there is some cases where this can be proved
Proof mathematically?
Yeah.
No.
I don't know, no, it's the same.
No, in fact, so there is this review article from the 2018 like International Congress of Mathematicians.
Yeah, I think that maybe in this case, Nalini,
Yeah,
I think that she proved that something, for example, you have this geodesic flow with a constant negative curvature,
yeah.
the unending quantized.
Yeah, that's right.
They take the Laplacian, etc., because it's easy to define everything in this case. And the eigenvalue have this type of.
I think the proof is for eigenstates unless I missed something like after 2018.
Okay,
So what Nagini's review article says, for instance, is mathematicians so far have been able to prove some statements like Schneider-Lagrange's theorem for eigenstates. Eigenvalues seem to be like much more hard to access.
okay,
And he also comments that it appears that the problems is impossible to tackle like or something of the sort. So there are like a lot of difficulties involved here. And which is why it's mostly physicists that have been looking at eigenvalue, because even the statement of the problem doesn't make mathematicians comfortable. Okay, so yeah, these are largely like numerical observations. There is some kind of semi-classical theory by Berry in 1985 connected to periodic orbits. The details of that is not like important here. But yeah, what the semi-classical theory does is essentially it gives you an argument for why this is likely to be the case in most systems. So that was about quantizing classically chaotic systems. But more recently, over the past decade, we've been finding a much wider class of systems where this kind of behavior is reproduced, including many body systems. This includes emergent quasi-particles, like effectively single particle systems and many body systems. Nuclei, which is kind of the original kind of systems from which random matrices were motivated, interacting spins, and more specifically, for instance, the SYK model, which is a specific model of interacting fermions. And quantum circuits, which is also a many-body system, but it's like if you have many qubits and you apply a deliberate set of gates to control them. And there are even like connections to like systems associated with black holes and quantum gravity. And in all of these cases, even though the structure of these systems is like very different, what happens is the eigenvalues follow these same random matrix trends. And as a result, we have to upgrade those observations to something that looks like this. Intuitively, quantum chaotic systems, whatever that means, we don't have a precise way of stating what that means yet, usually have a random matrix energy spectrum. Intuitively, quantum integrable systems usually have a kind of Poisson energy spectrum. But then the question is really, why should we even look at eigenvalues? And the justification that's normally given is that random matrix eigenvalues is a symptom of random matrix eigenstates, but eigenvalues are easier to calculate. So in some sense, random matrix eigenvalues should tell you that something like ETH is satisfied. But we don't really know if that's the case. That's just like wishful thinking in some cases, because eigenvalues and eigenstates of a matrix, they're like formally independent. You can have the same set of eigenstates, replace the eigenvalues with something that's almost completely different, and still get very similar behaviors. And overall, theoretically, what is the connection between random matrix eigenvalues and something that resembles chaos? And what about like other kinds of eigenvalue distributions? Here we have like only two specific classes of distributions. And well, it would be desirable to have some kind of general understanding of how eigenvalue statistics really like influence systems.
so in the case of integrable, it's proved.
No, again, it's not true. It's just that most integrable systems show this. Berry and Tabor have an argument for why that should be the case for most.
But there's no something that in integrable system you have the eigenstate. They are around certain invariant torides.
Yeah.
Therefore, there maybe some kind of discrete structure that can be analyzed.
Yeah, so
Maybe not Poisson, but at least some kind of.
yeah, so we know that there are specific kinds of structures. For Poisson, so that is in fact from this invariant tori kind of model. So that's the kind of model that Berry and Tabor start from, or at least that's the kind of picture they start from to get this Poisson out. Again, it's not like universal, there are exceptions. So it's again more of an argument. And there are systems where we can get like very specific energy levels that are neither Wigner-Dyson nor Poisson, they're in their own class. But they're like classically integrable, classically ergodic, and whatever. So like it's not a comprehensive picture. And that's also kind of what probably makes this problem interesting is we don't even really know how to begin to define certain things. So there's a lot of room to explore, but it's also like pretty challenging to explore.
What is intuitive with quantum chaotic?
That's exactly the question that I'm asking in this presentation as well, because that's what people usually say. But we can't really say what that means. In practice, what that would mean is an observable satisfy ETH could be one criterion systems, or generally if you have some kind of fast relaxation, that could be another. Or if you calculate node log, for instance, and find out it has an exponential decay, that could be another. That's why intuitively quantum chaotic. There's no like good way of defining that at this stage.
It's not that you see this Wigner-Dyson distribution and you decide that it's quantum chaotic.
Yeah, so that's another
That's
approach.
usually the logic.
That's another approach, and but then that just becomes a label you apply to a Wigner-Dyson.
Also, is it the full distribution that matches? Or is it maybe just the, the level of repulsion? Like, does the full distribution matter?
Okay, so there is some kind of refinement there, which is there are certain measures that need to matter. In fact, one of the things I'll attempt to address in this talk is which aspects of the distribution actually matter. But it is completely conceivable that some kind of higher moments don't have to agree with random matrices, for instance. And the kind of measures that I will argue will matter turn out not to be the level spacings, but something else, which is essentially this. So this kind of how much the fluctuations go around the regular spectrum, that's what I will argue actually matters.
Can I ask you, I'm just worried it's nice to have an interactive talk, but like I'm worried that we're not gonna get to your results. Can you give a brief summary of your results so that like.
Yeah, coming up in like 2 slides.
Thank you.
Okay. So just 3 slides. So just to like recap, because so far we've just been discussing the background really, because the background is like kind of complicated. In classical statistical mechanics, we have ergodicity in a phase space, which is a dynamical property, leading to the emergence of the microcanonical ensemble, which is a statistical property. And this is something that mathematicians understand really well. Quantum mechanically, it's kind of a mess relative to classical mechanics anyway. We have made a lot of progress, but there are still like several open questions. So we have 2 kinds of things we look out for: eigenvalue statistics, eigenstate statistics. This is simpler to state, which is eigenstate statistics lead to some kind of microcanonical ensemble. But this is valid only for specific observables, and we don't fully understand which observables it is valid for. So there's like an observable dependent statistical property, unlike the classical ones. Eigenvalue statistics is more complicated. So we have a lot of connections between Wigner-Dyson statistics, which is the random matrix eigenvalue statistics, and the presence of periodic orbits in certain kinds of systems. But there are systems without periodic orbits, which don't have chaos, but show ergodicity that also show random matrix statistics. So chaos or periodic orbits are not the whole story. And also the simplest ergodic systems, which is like 2D linear flows on tori, which would be the CAM tori with like an irrational frequency ratio. They do not show Wigner-Dyson statistics. So it's like ergodicity does not imply Wigner-Dyson statistics, but it can lead to one. So there's a lot of, yeah.
But it says, it shows that what was WD for WD?
Wigner-Dyson. That's random matrix statistics.
Okay, so you say that in this one, there are no chaotic, like ergodic system without periodic orbits?
Yeah.
But they
So,
still exhibit this kind of random.
yeah, some of them. So the standard arguments in terms of periodic orbit theory, like, well, it's called periodic orbit theory in physics. So those standard arguments, like, they don't necessarily hold for systems without periodic orbits.
If somebody give you a map,
Yeah.
whatever.
Yeah.
Born reserve, do you know how to quantize or there is some receipt?
Like how to quantize to get this kind of behavior?
Well, so yes, so some quantization, you say that there are many ways to quantify.
Yeah.
So there is some quantization that. For instance, you have an irrational rotation. The
Yeah.
most simple, that is ergodic and it's not chaotic.
Yeah, that belongs in this kind of system. That does not
And it
show.
don't show
Yeah.
WD.
So, okay, so finally getting to my result, which is in our work, we show that eigenvalue statistics corresponds to a form of ergodicity in the Hilbert case. So you have, it implies the existence of an orthonormal basis where like every state in the system goes over like every other state with sufficiently large overlap. And well, at least it's kind of like a simplified general picture of what might be happening with eigenvalue statistics. And this ends up being an observable and dependent dynamical property. So we're getting closer to imitating the connection between the dynamical property of ergodicity in classical mechanics and the microcanonical ensemble. So we have some kind of dynamical property representing ergodicity, something representing the microcanonical ensemble. But at the end of it, we still do not know how they're related because eigenvalues and eigenstates are independent. So this is what I'll be focusing on moving forward. Okay, so this is going to be a sketch, and so the sketch is really to motivate how we can define a quantum form of ergodicity that connects to energy levels. So yeah, the first thing would be I'll start classically. So in a classical phase space, let's not consider regular ergodicity, but let's consider like some kind of larger cells of the phase space. And intuitively, these are supposed to represent like blobs of minimum uncertainty or something like that. So it's kind of giving you a handle on the energy time uncertainty concept. And then we want to consider the motion of these cells of phase space rather than individual points and try to see what forms of ergodicity we can define based on that.
This is classical.
This is classical phase space. Yeah. So we just partition it into regions. And as they evolve, they won't like exactly evolve into each other. They'll like evolve into different shapes, and there'll be some kinds of overlaps that we need to track. And one thing we can do is discretize our notion of ergodicity in some sense to incorporate fuzziness. One motivation for doing this is once we have this kind of representation in terms of discrete cells, all kinds of invertible maps on these cells are permutations. And the only ergodic permutations that go around where each cell versus every other cell are cyclic permutations, because any other kind of permutations can be decomposed into like cycles that don't talk into each other. And then the kind of ergodicity we want to check for is whether the motion of each of these cells approximates a cyclic permutation.
Oh, wait, so you take a cell?
Yeah.
So this is a partition of your configuration space.
Yeah.
And then
Phase space.
eh?
Phase space partition.
Space, yes. And so you take one of your cells and you iterate your cell and your dynamics.
Yeah.
And when you plane it, this is only going to be a permutation of them.
But no, this will be close to a permutation. So here is an example in like a 2D torus. These are the cells, and as they go along, you can see that. So the gray part is the part that's like evolved in time. The blue part is the cell themselves. You can see that they start to disagree. So the question is it close to a cyclic permutation? Not if it's exactly equal to a cyclic permutation. Exact equality almost never happens except for something like a rotation on a circle. But what we want to see is whether it's close to a cyclic permutation.
And it's really confusing because many of those chaotic dynamics, they don't look like permutation. It's exactly the opposite.
Right. So here I'll just like point to some
Yeah,
mathematical study of something like this.
Uh-huh.
So Katop and Stepan, which is like some they have some paper from 1967 that looks at approximating dynamical systems by cyclic permutations. Now, of course, in practice, a lot of these can be constructed for some ergodic systems. It's much harder to construct them for like actual chaotic systems. I'm not sure if I'm aware of an example where it's possible to construct them for chaotic systems. So again, as stated here, classically, the justification may not be like very obvious for why we're doing something like this, but after quantization, it should hopefully be like more obvious. So yeah, they have some techniques and like this old set of math works, which use this kind of cyclic permutation approximation to prove ergodicity or disproving something. And from that, what we're trying to do is extract like two separate properties that we're just going to define as their own like discretized ergodic properties.
This type of example is exactly the one that they are not mixing. So
So you're working on the non-mixing, you're contacting non-mixing classes.
So it turns out that what happens after this. So there is a subtlety here, which is the kind of result stated by Katok and Stepan. They rely on some. Well, okay. Before actually going there, what I want to ask is, are you familiar with those results and are you discussing?
I'm extremely familiar
Yeah, okay.
with that of control.
Yeah. So
Most of the time,
yeah. Okay.
but don't.
So Katok and Stepan, they work based on some error, right? There is a single step error. And that single step error that can only have a certain kind of value for those ergodic systems. This is not based on a single step error. This is based on what happens as we go through successively through every kind of commit or every kind of cycle. And it is possible for the single step error to be larger than allowed. And so for instance, in like chaotic systems, you have the Ks entropy putting some kind of limit on the error. And even when the error is larger, it is possible for this to happen in principle. In practice, I do not know of an example. But in principle, the single step error does not provide a necessary condition for this property. It provides a sufficient condition, which is what Katok and Stepan have looked at. What we're doing here is we are extracting this property as a separate thing altogether, and its use or its generality in classical systems is not really clear. But again, the justification for doing this will be more obvious after we quantize. After quantization, it works even for like Bernoulli systems.
Okay, so you assume that you have a system that they have this kind of classical cycle ergodicity. It's not all systems are going to satisfy this, but assume that you have one.
Yeah.
And then you are going to generate a procedure how to quantize
Yeah.
the system.
That again seems very hard to do.
Okay,
So what we are going to do is we're going to assume that this property exists classically,
yeah,
use that to motivate separate quantum properties for a quantum system.
okay,
Connecting the classical procedure to the quantum procedure is hard.
okay.
And after that, we can forget about the classical kind of definitions because they're just to motivate the quantum ones. So again, just to recap these definitions, classical cyclic ergodicity would mean like every cell versus every other cell in a cyclic sequence.
Okay.
So we have like if we order them like C0, C1, etc., and if we consider C0, then all the way until C5, it needs to like visit each cell with sufficient intersection, and the same thing backward. Aperiodicity would be like not returning to itself, or more or less. There's a more formal way of stating it. And then what we can show is largely based on Katok and Stepan's proofs with the error again is cyclic ergodicity plus this condition that each region contains at least one cell, each region meaning each physical region of phase space, that implies ergodicity. And strong mixing implies that we have cyclic aperiodicity for every choice of cells.
Yeah.
And one thing to emphasize here is these are one-way implications. So they're not even necessarily equal, which is why it's kind of essential to separate out these properties as our central focus. And then quantization is again going to be like very loosely motivated. This is not about a quantization procedure. This is about how to quantize these notions of ergodicity for a giant system. So in quantum mechanics, we have the uncertainty principle, and so the n goes to infinity limit of there being an infinite number of cells here. That should be cut off at some point to represent the finite dimensionality of the Hilbert space. Formally, this is called Weil's law in some sense, or at least the leading term of Weil's law, which is that the volume of the cell corresponds to the number of quantum states for the object. And what that means is we can replace the classical n goes to infinity limit with just the number of pure states in a quantum system. So this figure can be formally replaced with this kind of figure where like each cell is replaced by a pure state. And this representation is something like the angular direction represents the pure states in the Hilbert space. The radial direction represents the overlap of a state with these pure basis states. And we assume that it's an orthonormal basis.
So yes, so you want to, this is actually happening, or you are assuming that when you quantify, you can produce this kind of partition on?
For now, we're just gonna assume that such a thing might exist.
Okay, it's not that this is happening because you quantify that system or something.
Yeah, so forming this connection rigorously is hard. In fact, even doing it at a physicist level is very hard,
Okay,
except for a specific kind of very simple system to write, for instance. But we're just gonna like motivate these properties in general. And then I guess this is one of the main like slides, which is we define quantum versions of these properties, which is that every pure state, every quantum state visits every other quantum state with sufficient overlap. And for sufficient overlap, well, one criterion is that we use the overlap of random states. So states that are randomly distributed over these states, they have a typical overlap of 1/d with each state. And so the criterion that we use would be that the overlap of each of these states would be much greater than 1/d. And that is for visiting each state. And for each state not visiting itself, which is a periodicity, we want the overlap to be not much greater than the random matrix value. So these are criteria for now. And so this condition just states that we go through one full cycle. And this condition is necessary through because of something called quantum recurrences, which if you wait long enough in every quantum system, you get arbitrarily close to the initial state.
Hmm.
And so to avoid that, you need to like cut off the time over which this happens.
sorry, so quantum synchronicity, you put CK plus P?
Yeah.
What is it?
Okay, so you start with state CK, and after P time steps,
PEC, okay, after P.
after P time steps, you want to find the overlap with the K plus
And
Q.
you want to be reasonably well correlated.
Yeah.
Yeah, the first one is like cyclicity. Cyclicity would be CK of PT0 equal to CK plus P. Here he's saying they intersect
Yeah.
consistently.
With a lot
And
of.
absence, aperiodicity is exactly like some kind of mixing. Like
yeah.
some kind of mixing.
Yeah, but
CK
mixing with
and
respect to
P
the
will
initial
not come to CK.
Okay,
Will be stranger from
so it's
CK.
not going to be overlapping with itself. So
Yeah,
it's kind of.
And all this is done at the level 1/d, where D is the dimension
Yeah.
related to the energy. Okay,
Or the energy band.
what does it mean energy here? Because we're talking about the dynamic system, right?
Yeah.
So what do you mean by energy?
So quantum mechanically, when you have a Hilbert space, you have some energy eigenstates that kind of. So for a Hamiltonian system, you have these energy eigenstates, and D there would be the number of energy eigenstates that span this Hilbert space.
So usually that means that the generator of the dynamics is the Hamiltonian, whereas you're not specializing to how you generate the dynamic.
So it's time independent unitary dynamics. So there's either a Hamiltonian or you can define an effective Hamiltonian. So yeah, you can think of these as quasi energy eigenstates, for instance, and D is the dimension of the Hilbert.
So that's one. Can I just ask you, so the idea, should I be thinking of quantizing, this being applied to quantize single particle problems, or you don't care?
Any system with a Hilbert space. So many bodies, single particle.
Because if it was a single particle problem, I would say, well, why not use some wave packets, coherent states, or something like this?
Yeah, so
Is that similar? Because, those things will also have similar properties.
yeah, so they have some issues, which is that
You don't have, if that's not on your slide, let's just keep going, because I want to see what else is coming.
so we define these properties in terms of assuming the existence of a basis, and that's how we also get observable independence, which is instead of talking about a specific basis, promote these statements towards saying that a quantum system is cyclic ergodic if there exists a basis satisfying this property. And a quantum system is cyclic aperiodic if there exists a basis satisfying this property. And then we can ask the question of which choice of basis states is optimal, or even which choice of time step to cycle over. And again, I'm going to be like hand wavy here, which is
Does it matter which choice of basis?
that's how we're going to like connect to
Your
energy levels.
definition doesn't care what basis you use.
Yeah, so the definition does not care which basis we use. That is how observable independence should work. But still in practice, if you want to check if a system shows these properties or not, it would be good to have some kind of basis to go to check those. And so when we actually do that, one way to motivate how to do that is just to like argue in terms of some classical quantum correspondence, which is classically when we discretize the phase space and talk about cycling through those states, it's almost like the cyclic commutation is measuring time. So as you go from C0 to C1 to C2 and so on, the label of the CK that kind of measures the number of times steps of evolution. So in quantum mechanics, we can motivate that the appropriate basis would be something that represents time in some sense. And because energy and time are considered conjugate variables, and conjugate variables in quantum mechanics are related by Fourier transforms, the optimal basis would be the discrete Fourier transform of energy eigenstates. There's a more formal justification of this, but there's like a shorter one for the slides. This is like a formal definition. So we start with the energy eigenbasis, apply a discrete Fourier transform, taking this as a function of n. And this is the output, and this would be the optimal basis. And through some kind of similarly qualitative reasoning, the optimal time step would be like the minimum time it takes for a change to happen in the system, which would be like 2 pi over delta E by the energy time uncertainty principle. This can again be justified more formally using, for instance, the spectral form factor. So what we have is we have a kind of choice of basis when these properties are most likely to happen. We can prove it for aperiodicity, almost prove it for ergodicity.
Second, the last part of the sentence.
So we have a choice of basis where the properties of cyclic ergodicity and aperiodicity are most likely to be seen, which is this one.
But wait, you don't, the eigenvalue do not appear in the formula?
No, because there's a discrete Fourier transform. So instead of En, these should be thought of as like labeled by N instead of being labeled by En. So N shows up here.
What do you mean optimal? I'm stuck on this word.
Optimal meaning most likely to show these properties. Formally, one way to do this is to define 1 minus this as some kind of error, and then try to optimize that error by like rotating the basis with units.
So you're saying these new states that you defined as CK,
Yeah.
they satisfy the two hypotheses, the cyclic and the aperiodic?
Like they are the ones that are most likely in a given system.
They are the ones that are meant to like. Okay.
So if you want to see if a system satisfies both properties, these are the states that you should check first, because they are most likely to do that. And there's a time step that you should check first. Again, there are exceptions. So this formal justification works for that one kind of systems. And now let's look at the connection to energy eigenvalue statistics. So once we work with this kind of state, we kind of naturally get a connection to the energy spectrum because these are the energy eigenstates. And if we want to measure this particular overlap, start with CK, evolve it with P steps, and compare its overlap with CK plus P. Then that is given by this expression, which is just a sum of phases, like just plugging this into this expression, together with the fact that the En are eigenstates of the time evolution operator. And this sum here is essentially the Fourier transform of the distribution of these quantities delta n, which are the differences between the energy levels and integers scaled by a suitable quantity. And this is a good thing because when we looked at eigenvalue statistics, we noted that one thing that was different between random matrix statistics, Poisson statistics, and regular spectra was the size of fluctuations around this integer spectrum. And this is kind of naturally appearing here once we start considering these cyclic permutations. So one intuition for this connection is that a cyclic permutation operator has eigenfaces that are regularly distributed according to this. Because when you act d times with the same operator, you need to return to the original state. So it has to be roots of unity.
Wait, sorry, you have some rank ordering thing going on this? Like the E0 is the smallest energy eigenstate?
Yeah, E0, E1.
So you are more likely to succeed in satisfying the condition of this definition if you are in the regular.
Yeah, the regular case is
Regular
perfectly
case.
ergodic. It just cycles through.
Sorry?
The regular case just cycles through all the states. So it's perfectly ergodic by that definition. Aperiodicity, the regular case violates it because it keeps returning to the initial state.
Yes, so you miss the aperiodicity.
Yeah, so
It depends
optimal.
on which,
So what happens in the regular case is this is still the optimal basis, but the fact that this basis is not aperiodic implies that no other basis in the system is aperiodic.
okay,
So that is the sense in which this is optimal.
okay.
So here we get a connection to the regularity of the energy spectrum. And one thing I'd like to remind you here again is that for random matrices, we had a square root of log D. And for Poisson spectra, we had a square root of D. And now let's look at where the square root of log D actually comes from a dynamical sense. Yeah, before that, this intuition is,
Wait, why is delta? Delta is 1 point function of the distribution.
it's not a 1 point function, it's the size of these fluctuations.
Delta is just a shifted eigenvalue, right?
Shifted by its order in some sense. So this n kind of contains all the other correlates. It would be a 1 point function if it were an arbitrary energy.
Yeah.
But I want En to be correlated with its position and the order of energy. And that brings in the rest of the correlations.
Like you ordered the first D eigenvalues.
Yeah.
In increasing order.
Yeah.
And you associate to each one n over D.
Yeah,
And you look at the delta.
yeah.
And then if it is Poisson, I guess you will not have the cyclicity.
Yeah.
Right?
Yeah, so that's what I was gonna
That was what Enrique was mentioning. The cyclicity, you don't hope to have it under any mixing or chaotic.
Yeah, but Poisson systems are like the non-chaotic ones. These are the integrable ones.
Sorry.
Random matrix ones are.
Yeah. So in Poisson, you expect to have that property?
No, you don't. You don't have that property.
And so in the regular, you expect to have nowhere, in which one?
So you have both properties in this one,
In the middle.
in the middle.
Okay, good.
Yeah.
So in Poisson, you have aperiodicity, but not ergodicity.
What was here?
What?
CUE.
So CUE is just one of the random matrices.
Okay.
One of the random matrices.
Circular ensemble.
Yeah, circular.
Yeah, because Poisson is the very table conjecture that it is the integral.
Yeah. So the intuition here is essentially that a unitary cyclic permutation operator has its eigenphases as roots of unity. So measuring whether a quantum system acts like a cyclic permutation of basis states is essentially the same as measuring if its spectrum is close to the spectrum of this cyclic permutation, which is essentially this. So this is the spectrum of a cyclic permutation of And I guess the main quantitative demonstration of this term is the fact that we can derive random matrix eigenvalue statistics from these conditions. And just to like sketch the derivation a little, the delta n, which are these deviations of the energy levels from the regular spectrum, they tend to be distributed as a Gaussian. And numerically and analytically, that seems to be the case for the random matrix ensembles as well. So we write down the Gaussian form of these overlaps Zp. And a random state has Zp squared going as 1 over D. So for cyclic ergodicity, we want Zp squared being much greater than that. For P time steps, where P at least goes up to D over 2, so that it covers the cycle both in the future and the past. For cyclic aperiodicity, we want that when we return to D, so when P equals D, this overlap must be smaller. What this means is the Gaussian up there, that should remain large until a time of D over 2. But then decay to a small value by the time of t. So just putting the simple conditions in, we get a constraint on this parameter delta, which is the size of fluctuations of the delta n. And that constraint is just that it has to be between these two values. And we see that the square root of log d kind of comes up here naturally. There is an exponential here, taking that to this side of the log, and square root for the delta, that's how the square root of log d comes, which is quantitatively how fluctuations behave in random matrix ensembles. More specifically, there are concrete values for the random matrix ensembles. So the three popular kinds of random matrix ensembles are like circular symplectic ensemble, circular unitary ensemble, and circular orthogonal ensemble. They have these values which are pretty much precisely in this range more or less. So what we can do right now is we can have like precise ergodic properties and the quantum Hilbert space, and we can derive random matrix eigenvalues from just assuming this Gaussian.
Although, like, what if you have a spectrum like the
The hydrogen atom is integrable.
um,
So these fluctuations would be
what are the energy levels again? I don't remember.
1 over n squared, right?
Yeah,
So you have a lot of degeneracies.
so what, you plotting delta, it's the difference, one over n squared minus n. And just-
Yeah, but there'll also be
Eventually
degeneracies.
becomes regular, right?
No, there'll also be degeneracies.
Uh,
So it's like there's a lot of energy levels that correspond. There's a lot of n's that correspond to a single energy level.
Yeah.
So the fluctuations will actually be large and something closer to this.
So I don't understand how come the properties on these CKs and the dynamics of them
Right.
are related only to the distribution of the eigenvalues, the n and not the eigenstates themselves. So they disappear completely from the.
Yeah,
They used to be in the formula for defining the CK.
yeah,
And now you're telling us that the properties of being cyclic, aperiodic, etc., are just properties of the distribution of the eigenvalues.
Yeah.
And no more eigenspace.
Yeah.
How?
So in this formula, if we plug in the CK here, we get this sum. And for CK plus P, we get something similar with K replaced by K plus P.
Yeah.
And then we'll have a sum of ENs on the right hand side, sum of ENs on the left. And then when EN and let's say ENs here and EMs here, and M and N are unequal, they'll be orthogonal, so that will give you 0. When N and M are equal, they'll be the same state, so that will give you 1.
No, I understand the formal explanation, but what I don't understand is, so now you're gonna describe the quantization of the system,
Right.
some properties, I don't know what.
Right.
With just understanding the distribution of the eigenvalue.
Yeah.
That's it.
So this is in fact kind of what just to get back there. What I was trying to motivate here, which is eigenvalue statistics, would correspond to a kind of quantum dynamical property in the Hilbert space, which is observable and dependent. And eigenstate statistics will take care of what depends on observables.
Was that was a simulation that you showed there? Or what is that? It's just a picture?
This,
No, before? No.
the fluctuation. Oh, this,
Yeah, that.
yeah, this is a simulation. I'll get to something like this towards the end, which should be like very short.
Okay.
Okay, so one way to think about why it's just eigenvalues and not eigenstates is because we're talking about the existence of a property in the Hilbert space, which does not rely on any basis. The existence of a property. And eigenstates are only defined relative to some basis. And since you're talking about the existence of a property, we need like values that don't depend on any basis. So we need like invariants in the Hilbert space, which are the eigenvalues.
The logic is not about for any set of CKs. It's really just for this specific CKs that you're defining.
So, okay.
But they're like the optimal ones.
But
To do what? At the end, okay, suppose it works, so what do you conclude?
So from this, what I can conclude is random matrix eigenvalue statistics. The kind of dynamical property that corresponds to is visiting basis states in the Hilbert space in the cyclic sequence.
The algorithm properties on this basis CK.
And because we have such a basis, that means that such a basis exists in the Hilbert space.
Okay.
So yeah, so it's essentially random matrix eigenvalue statistics means the existence of a basis where you have this ergodic property.
So let's say, give a definition. I am cyclic aperiodic. I'm going to say I'm cyclic aperiodic on the Hilbert space if my operator U hat has a basis on which I can define these two things. And you're telling us if the spectrum has some property that resembles random matrices, I am cyclic aperiodic.
Yeah.
That's it.
Yeah.
And vice versa.
No, there are more general factors that will give you these properties. So for cyclical goddessity, we will see some examples shortly. But yeah, the takeaway here is one question was what do random matrices actually represent, and we have some kind of dynamical property for that. So there is this quick intuition slide, which maybe I won't get into in too much detail, but the recent random matrices have to sequentially visit an orthonormal basis. Is essentially because of this level repulsion, where well, let's just so there's some motivation here, but the random matrix distribution depends on the difference between eigenvalues to some power. And if you do this for every set of pairs of eigenvalues, then you get this determinant. And you can think of every row in the determinant as one of these CKs, or rather the evolution of C0 at each time step. And the determinant measures the volume of each step of evolution. So what the random matrix distribution is actually kind of trying to measure is whether whether the evolution of the C0 state is goes in an orthogonal way, because the determinant kind of measures the volume of the rhombus that you get from combining all these states. So already the hard distribution of random matrices is telling us something about visiting an orthonormal basis. And what I've discussed so far was like a more quantitative way of getting to that, but this is some kind of intuition for that.
So can you go back? Yeah, can you give us more of an intuition of the eigenvalue repulsion?
Okay, so let me then actually just
The level repulsion.
yeah, so these random matrix ensembles, the way they're defined is usually you have some eigenvalues.
Yeah.
And then you act on them with all possible unitaries or subgroups of the unitary group. So for CUE, it's all possible unitaries. For COE, it's all possible orthogonal matrices. CSE, all possible unitary symplectic ones. And when you do that, the probability measure is like the number of new matrices you generate by doing that. When you have degenerate eigenvalues, and you act on them with unitaries of this kind, you can just factor out this eigenvalue. So these eigenvalues are identical, and there's just the identity matrix. So V and V dagger within the degenerate subspace give you one. What that means is you recover the same matrix. So by acting on these eigenvalues with new unitaries, you're not generating new matrices. So the statistical weight of these degeneracies in the ensemble is 0. And then using a scaling argument, you can also show that some power of the difference between eigenvalues. So that's how you get level repulsion. And then doing this for every pair.
Wait, sorry, you can do this for arbitrary eigenvalues? That's the point.
So for degenerate eigenvalues, you don't generate new matrices.
But for regular eigenvalues.
For regular eigenvalues, you do, which is how you get this difference. So here the statistical weight is 0. So when EA equals EB, this becomes 0. But using a scaling argument, you can show that it's also some power of the difference for regular eigenvalues. And so for arbitrary eigenvalues, taking all such pairs, we get this determinant form. And this is called a random one determinant, and it's one of the standard results of random matrix theory. But the fact that we have a determinant here, which seems to track the evolution of the C0 state, means that the random matrix distribution favors a system where a state evolves into orthogonal versions of each other. Because loosely speaking, the volume of this rhombus is maximized when all its vectors are orthogonal.
Sorry, there's C's here, there's E's, I don't know if those are connected, I don't know, there's also random matrix here. What's the metaphor and what are you trying to compare it against?
Okay, so I'm trying to motivate why a random matrix has to visit an orthogonal basis.
Why a random matrix has to
show the property of cyclical goddessity, independently from that calculation that I showed you.
forget everything and then just focus on this.
But there's just intuition. We can't quantitatively derive the level statistics like we could using cyclical goddessity, but this is like motivated.
You're saying for any distribution of energies.
This is the hard distribution.
But in the previous slide, you said you can have any distribution of energies. Give me a set of energies, and then this is the P of Q.
Yeah, but then the probability measure is determined by the number of matrices you generate from each set of energies. So for a set of energies, you can assign a probability based on how many matrices you generate by doing this. And that is kind of the random matrix distribution. That is the distribution that gets you the weighted eigenvalues. And
But for fixed set of energies?
You're trying to determine what the probability measure is for a fixed set of energies.
Okay, so
So you take-
fix the energy.
You fix the energies. And then you take every possibility for these fixed energies. And then you get a probability distribution that is a function of which energies you have. So you get a probability distribution on the energy eigenvalues. So you fix the energies, you determine the measure for each energy, and then change the energy of fixed until you get a function of the energy eigenvalues for every choice of energies.
No, you start with the energies. You're saying you start with the energy.
That is one way of looking at it. Another way of looking at it is just you start with this hard measure. Which
Yeah, that seems the more natural way, and then you, from that, you get a distribution of energy, of eigenvalues or energy.
Yeah,
levels, right?
Yeah, but this is kind of motivating why you get this. So this is the distribution you get
Yeah,
from the hard measure. And this argument is motivating why the hard measure corresponds to a distribution that looks like this. In the previous slide. Or yeah, I mean, if it's not that obvious here, this is basically the main quantitative demonstration, which is that from the ergodic dynamical property, you can get these like precise random matrix states.
I mean, we're up against lunch, maybe take 5 more minutes. And
Yeah,
we'll Continue, especially with all these questions.
Okay. So, what I'm gonna do here is just some animations to show how this actually happens numerically. So there's a representation of the Hilbert space where the angular direction are basis states. The radial direction represents the overlap with these basis states. And I'm just gonna evolve like C0 and see how it evolves. Blue will represent how C0 spreads over the Hilbert space, and red will just track the cyclic part of it.
so you're involving it with random unitary.
Yeah. So as it goes along, the key thing for ergodicity is that it decays to this random matrix value, which is the inner circle. Or it doesn't decay to that value until it covers like half of the Hilbert space in both ways. So yeah, it kind of decays around here, which means that it's ergodic in this sense.
What's the red thing supposed to show?
The red thing tracks the component of this blue thing along the cycle. So after P steps, what the component is along CK plus V.
And what's the blue part?
The blue part is the evolution of C0 itself. What its overlaps are with each of the basis vectors. Only 8 basis vectors are shown here, but there's like 256 of them. So 256.
Listen again, so first you do the evolution of C0 and the blue.
Blue is the evolution as well. So it shows you the overlap of C0 with each of these basis states.
Okay.
Red
The
tracks
red-
the cyclic part.
I'm sorry, and the red.
The red tracks the cyclic part.
Okay.
So how C0 at time t, what its overlap is with CT.
What is red, what is, what is green, what is, what do you depict? It's vector in your.
Yeah, this is the initial vector in my
I'm
Hilbert
gonna
space.
write down the equation, so we know what's. Or maybe there's no marker.
If you tell us.
Okay, so I say.
We have these states.
Yeah.
Yeah.
You
We have
depict
these
them,
states,
in atom. What does it mean depicting them in atoms?
So what I'm doing is the radial direction here represents the overlap of a state with the corresponding basis vector.
The norm.
Okay.
The overlap. So if I have a state psi,
Yeah.
then the radial direction here would represent the overlap of psi with this state.
Okay, it's like you take any guy in the Hilbert state.
Yeah.
And you project it on this basis.
Yeah.
And the radial thing will tell you how much he takes on the direction C0, C1, C2.
Yeah, in a cycle. And the blue is the
Any
whole
cycle
cycle.
inside.
So in the first time step it's C0, or like at time 0 it's C0, time 1 it's C1, time 2 it's C2. So red
This
plus-
is how you define your basis, C0, C1, C2.
yeah.
What do you mean in time 1, time 2?
So at the evolvement in time, it keeps exploring different.
Who's evolving in time?
This, as this happens,
This is C0.
yeah, this is C0, it's spreading out.
You keep multiplying C0 with the random unitary.
Yeah, with the same random
Okay,
unit.
and the red thing is
The
the
cycle.
evolution of C0 in time.
The evolution of the component of C0 with respect to C0 plus P at time P. And it just shows you that it explores the full Hilbert space before decaying to this random value. So this random matrix case is ergodic numerically.
So you're plotting a complex number, right?
Overlaps. overlap, so magnitude of that.
Okay, what's
Let's
the
say,
phase? Yeah,
It's the magnitude, real magnitude.
but what's the phase? There's a circle, it's a circle, right?
So the angular direction is different basis vectors.
Oh, so it's not continuous, it's just like this.
Yeah, it's a discrete, like, set
Got it.
of two vectors.
so we take C0.
Yeah.
And we iterate it in time.
Yeah.
And we plot an array. Let's say what are we plotting here? At each second, at each moment.
Yeah.
we plot
The overlap of C0
with
with CT, where T is time.
exactly.
It's a clock, so
Yeah,
there's
yeah.
T0 and then. it
So
goes-
at the beginning, C0 is acts as 0,
Yeah.
and then at time 1, he's very close to C1.
Yeah.
And then he's still close to C2, and he
Yeah,
starts
yeah.
going less and less.
Yeah.
Parallel to them.
But then it goes, and then it goes back exactly to C0.
No.
Yeah, but by that
Yeah,
time it's
yeah.
decayed, by that time it's spread out. So by that time it's decayed.
What is the blue then? Yeah.
The blue is the evolution of C0, but it's overlap with all states. So to play this again,
Initially.
Right,
you can see that the red track
just
blue
the
along
spikes
one of
at
them.
C0.
I didn't get that.
Initially, it's just the segment that sees.
Yeah.
Yeah, but then it spreads out over all states and time evolution. Because it evolves in
So you're
the.
telling us red shows cyclicity and blue shows aperiodicity.
Blue shows all overlaps, red shows cyclicity.
Do I understand, again, I'm thinking in terms of weight packets, like you're starting with a packet and then it
Yeah.
just spreads out.
Yes,
There's quantum
absolutely.
fluctuations as
Yeah,
we move
But
in
it's
time.
going in two directions, it's going.
Going in all
towards
directions.
Plus T and minus.
Yeah, minus T is just to track the evolution, so blue evolves only in plus T. Minus T is to show the completion of the cycle, so this part goes like backward in time.
Okay, it's,
Okay.
so if it's going forward, it does actually do this like loop around the origin and then it goes back.
Yeah, so
No.
it does this forward in time, it does this backward in time, so overall you've visited all states.
So it stops here, you mean?
It stops.
It stops here.
Well, now it's back.
Yeah, but then after
So
that it
it
continues.
starts very correlated to itself.
No.
It is correlated to what? And here it loses.
Yeah.
Because it's aperiodic.
So this is ergodic and aperiodic, and this random matrix statistics. For Poisson statistics, it just decays immediately, so it does not explore the full Hilbert space, but it's also aperiodic in that it never returns to itself.
How do you generate the dynamics here?
So take the CK, choose eigenvalues from a Poisson distribution, and then just evolve according to those eigenvalues. Because the CK are just the Fourier transform to the end. So this is an example of a system that's ergodic and aperiodic. There's an example that's non-ergodic and aperiodic. And then there are these systems which are not aperiodic. So this here is an ergodic system, which is this linear flow on a torus with an irrational frequency ratio. This is ergodic but not chaotic and not aperiodic. With the rational frequency ratio, we just get like periodic orbits all over. And these systems do not show random matrix statistics. Their level spacing distributions are like delta function spikes, not random fluctuations. But when we apply this, we can prove stuff with this, but I'm just going to show the animations here. So on the left side is the ergodic torus system. What happens here is it continues to explore the full Hilbert space being ergodic. And there are these spikes that keep returning to the origin, so it's not aperiodic. And for the rational torus, which is just periodic orbits, we get an exactly periodic evolution that still fails to explore the full Hilbert space because it does not have a significant overlap with most of the Hilbert space. And the overall takeaway from all this is we can consider the space of quantum dynamical systems, talk about two like dynamical properties, cyclic ergodic, cyclic aperiodic, and find at least one example of each kind of system. And so we have like a direct connection between quantum dynamics and eigenvalue statistics without relying on comparisons.
So the quantum procedure, so this is the Iguana rotation or Iguana translation,
This is an irrational flow on a torus.
Yeah.
So what does it do? Can you repeat on the quantum level? What does it do?
So it explores the full Hilbert space.
C0 turn and immediately spread or what happens?
So it explores the full Hilbert space. So,
It explodes. Yeah.
um,
Yes. So when you say it explodes, you see it in blue or in red?
So red tracks the exploration, blue tracks the overall wave packet.
Sorry, can you repeat?
Red tracks whether it explores along the cycle,
Yeah,
and blue tracks its overall distribution in the Hilbert space, which also keeps returning to C0. So this is like ergodic because it does this, and not aperiodic because it keeps returning.
yeah, without losing. It keeps returning, you mean the blue
Yeah,
line
there are blue
will come
spikes.
and be very long.
Yeah, so these keeps spiking up there. And this is kind of consistent with these tori being ergodic and not mixing. So these recurrences are like not mixing. And we can see that at the quantum level now.
And in the periodic one.
The periodic one, it keeps returning to the origin, which is because classically it's also like exactly periodic.
Yeah, and it is not ergodic.
Yeah, it is not exploring.
It doesn't explore. Ergodic means that this red line goes very close to.
Yeah.
But here you don't go to this guy, for example.
Yeah, so the cutoff is this circle. So as long as it's like significantly above this circle.
How do you decide what is the cutoff? Why this circle and not this circle?
Because this corresponds to a random state. A random state would occupy this circle.
Where? This one?
Yeah.
Here.
Can I propose we do this with blood, with sandwiches in our hand? Can you start, well, just a minute, can we probably, yeah, can you put up, if it's like, let's wrap up
Yeah.
and then, we.
So there's more like, I guess, just a summary of what all this can help with, which is, well, with cyclical aperiodicity, we can kind of come up with some speed limits, which are like tighter than some known speed limits, and provide some time limits on scrambling. So this has like some kind of direct implications. Cyclic ergodicity kind of quantizes a fundamental quantum dynamical property, allows us to talk about quantum dynamics without random matrices. But the question of how to observe it is separate, because the discrete Fourier transforms of energy eigenstates can be very hard to access in many body systems. And separately, another effort is like for eigenvalue statistics and eigenstate statistics, we have some ways to measure them, at least in present day many body systems where the effect is not too small, that's a subleading effect. And we have some theory proposals. So one is by like Peter Zola's group, and one, well, we collaborated with them for another, which is being implemented in a trapped ion system right now. And obviously working on it and it should appear in a while. And just another like quick summary is, this is one kind of ergodicity. There are other forms and radius systems that connect to different things. So we looked at like unitary systems which have energy eigenvalues. There are other kinds of systems where you can look at individual observables, Lindbladians, or just ergodic exploration of the Hilbert space when you have time dependence. And we can ask the broad question of, these are different pieces of this quantum statmic puzzle. We don't understand how they interconnect. These eigenstates, what I've described in this talk, how do they actually like present a coherent picture of quantum statistical mechanics? That's still very much an open question, and it doesn't look like we have any clear intuitive case going forward. So it's likely going to be like very challenging. Yeah, that's my talk. And one takeaway question, irrespective of all the details, just for everyone, is one simple takeaway here is, given a quantum system where each state on an orthonormal basis with every other state, what can you do with it? And what I'm really asking by that is, if you have a system that's cyclic ergodic, what are the direct consequences of it? We know it connects to eigenvalue statistics, but what about the physics of it? Yeah, that's the takeaway question.
Can you give an example? Short question. Yeah. Can you have a classical system that is quantum cyclic ergodic? Because you showed us K-tori, they're not. Chaotic system. No, K-tori are ergodic, but they are not a priori.
Yeah.
I'm asking, cyclic a priori. You have a classical mechanical system that quantized become cyclic a priori.
Which is most of them, like Sinar billiards, for instance.
Sinar billiard?
Yeah, any kind of billiard system that shows like regular dice or random.
That's very fun, because you see, Sinar billiard and classical level are way far from being cyclic. They are the opposite of being cyclic. A priori,
yeah.
okay, but they are not cyclic. And you're saying that on the quantum level, they become cyclic.
Yeah.
So sine, everything is.
Yeah.
Everything is loaded on the continent. So this one is loaded in the class. So you take the chaotic system, another system, you look at.
But they are not big.
You add in value to this one. Then you check. And therefore it will be cyclical.
Yeah,
But
because they are not simply a periodic on the class.
nothing, it's exactly the opposite.
That is in fact one of the things I found very surprising about this as well. Classically chaotic systems just spread out.
Yeah, there is no secret. The case, this secret periodic, it's very rare.
I'm actually close.
I have it like
Yeah.
the rational calculation. Or you're not secret. There is no way of.
You say four should support 10 years to the year. Calculation breakdown.
Okay.
By just now, you can.
Not,
Can I actually clarify one thing?
so the funny thing is that when you want to say.
So the mind definition is something to do with.
No.
It's not exactly.
Crazy to you?
Yeah, but it's not.
You do the partition.
Yeah,
You do partition.
This-
Okay, then if you look at all.
This is kind of cyclical. And you intersect an egg on it.
So by and like and it's not.
So
Yes.
then normally.
This one, that one over here.
Yeah,
This, this particular point, right, all.
Yes, you can hear.
That's here.
Yeah, the Russian rotation,
Yeah.
these are moving out.
Yeah, but that you can. If you want and to do it, like one of
Well, I agree.
And this is more like this.
Which is. That is.
It's all around the world. No, so you don't get, no. Basically, no. Basically, no, I'm sorry.
Quantitative.
Basically. No, this is not. This is. No, okay. Taste that I'm not gonna cover everything that KMT will cover. But I'm going to try to be sufficiently broad to tell you in various aspects how the theory was applied. So the KM theory is about linearization of nonlinear dynamics, make them look like a linear system. And when you do this linearization, you meet a problem called small divisors. So you need arithmetics to control the small divisors, but when you conjugate your nonlinear system to a closer to a linear system, you lose derivatives due to the small divisor. And you compensate this loss of derivatives with the quadratic scheme of successive conjugates. This is the Kolmogorov method. It is like applying a Newton scheme to a conjugacy problem, to a local conjugacy problem. You start with a linear system, you perturb it, you want to conjugate to the linear system, you get an equation to solve. If you could solve it in the same regularity without loss of derivatives, you would apply just the fixed point theorem in the functional space, and you would get a conjugacy as a fixed point. But you can't, because you lose derivatives, it's not compact operator, the inverse of the linearization of the conjugacy is not compact, so you have to counter these small divisors, and this effect of the small divisors is not like it's as old as mechanical systems were studied. I mean, in the initial stages, astronomers in the 18th century, they met these problems of small divisors, and Kolmogorov was the first one. Not really the first one, because Ziegler before him had attacked the small divisors with success in some cases, but he, let's say, opened the way to attacking them and neutralizing them, even in the very complicated problem of the n-body gravitational system. Okay, let me become more explicit now. I'm gonna tell you what are the topics I want to discuss. I'm gonna give a plan of what I'm gonna discuss, and then I'm gonna spend like 10 minutes for each topic. And if you want, we can skip a topic or add a topic, you just tell me. So one, I want to talk about Km, rigidity of linear systems. Two, I want to call Km reducibility of linear ODEs with quasi-periodic coefficients. So this is like you have a linear ODE, x dot equal ax. A is quasi-periodic. You want to conjugate it to a constant P, where the matrix A does not depend on time. So in fact, you want to solve linear ODEs when the coefficients depend on time. Three, Km stability of integrable non-degenerate systems. This is like I take a Hamiltonian, it's completely integrable, I perturb it. I want to see what happens. Does it continue to look like an integrable system? Yes or no? To which extent? 4, Km stability of integrable degenerate. So non-degenerate means that when you disintegrate your system, your integrable system, you look at the invariant tori, they carry frequencies. When these frequencies see all the phase space and the action variables, like when you see all the directions of your space, you call it non-degenerate. When you don't, you call it degenerate. In both cases, you want to have survival of the integrable picture. Hamiltonian. 5, I want to talk about Km stability around elliptic equilibria. 6, I want to talk about effective stability. So Km theory addresses stability for all time, asymptotic stability. But in physics, sometimes you know that you cannot achieve understanding for infinite time, and you say, if you tell me that you understand my evolution and you control it during 10 times the life of the solar system, I'm happy. And that is effective stability. So it's stability for long time scales. 7, counter Km. In fact, counter Km will appear in all these points. Every time we'll talk about the Km result, we will say what is its limits, when does it stop being true, what is necessary in its hypothesis of this kind of result. And 8, did I have? Okay, I need to talk about diffusion, which is also like counter Km, right? And 9, I just want to tease you with it. I'm gonna talk about entropy, but I mean chaos. That is our plan. Let us start. So what do I understand by Km stability, Km rigidity? So I started by telling you, take a linear model, like X maps to AX mod 1 on TD. You know what TD is, like the circle times the circle times the circle, T times. And I take this map plus some B. B is a vector in RT, B in RT, and A in SL, B phi. It's a map. So for example, A equals identity and B equals alpha. So you get X maps to X plus alpha mod 1. It's the rotation. Yes? And the first remarkable result on that I want to discuss. I'm not going to cite a lot. This is like an informal speech I was told. So we're not here to give credit to anybody. We're here just to understand the theory for people who don't necessarily work in KM. And in thermal dynamics, they don't care about who is what. They just want to know how it works. Anyway, here, this is Arnold in the 60s. He showed that. Consider a perturbation of R alpha. I'm going to call it. So like R alpha plus epsilon delta F. This is a map from TD to itself. This is what I promised you. This is linear, affine. Linear, affine, okay. Perturbation, nonlinearity. Epsilon is small. What can you say? So let me say the theorem is the following. If F volume preserving to and integral of delta F on the total, if 2 epsilon, delta F is smooth, 3 if alpha is Diophantine, 4 if epsilon is small, there exists H in this infinity of the torus TD such that H F H inverse equals I. So do you see here below, or I shouldn't write so low? Anyway, what I'm saying is I have 4 hypotheses on F. It is smooth. Yes. It has what is interesting for me is not that F is a volume preserving. What is interesting is this. What I'm saying is that F on average sees the rotation number alpha. The average displacement by F of orbits, of points, is alpha. That's what I want to see. Just this. If it is smooth, if alpha is Diophantine, and here I'm going to put Diophantine because we need it all the time, alpha in dc gamma tau, it's if for any k in zd minus 0, k scalar alpha minus L in N and Z, sorry, is bigger then gamma over K to the power D plus tau. I can put tau here, but to make it Diophantine vectors for them to exist, I need tau to be larger than fact. DC. So, and DC tau is just the union over gamma positive of DC gamma tau. DC tau for tau strictly larger than D has full Lebesgue measure. Okay, so which means that the Diophantine hypothesis is natural. It is typically satisfied by a translation vector, by vectors in R. If the translation vector is Diophantine, then for sufficiently small perturbation, I'm conjugated to the affine model. And the proof is the following. The proof is I look for H under the form identity plus H, right? And then I say, what should I prove? I should prove that HR alpha minus H equals delta F. If I prove this, this would imply that H F H inverse is equal to R alpha plus epsilon squared. So I started with R alpha plus epsilon and I conjugated to R alpha plus epsilon squared. Or if you want, I can write it even differently. If I linearize this equation, this is a nonlinear operator on the map H. If I linearize this, the fact that this is equal to R alpha, this is the linearized version. So if I solve the linearized version of the perturbative thing, and if this H is comparable to delta S, then I can apply the local inversion theorem and solve the equation. However,
Would you repeat the rationale for the first two lines?
okay, so I write here and I try to solve H F H R alpha plus delta F, yes, equals R alpha H.
Why are you trying to solve that equation?
Because I want to linearize it. I want to solve my theorem. I want to find the conjugacy that the conjugacy is like when you put eyeglasses to see the world. The conjugacy will you have your torus here. These are the orbits by the rotation, and you have your torus here, and these are the orbits by F. The conjugacy sends this picture to this one. With the eyeglasses of H, when I, instead of seeing the point X, I see the point H of X, then iterating F here, it's like iterating R here. That's conjugacy. It's like when you conjugate a matrix, P inverse A, P equal B, it means that B is A. Just by change of basis. Here, it's just like you're changing. Suppose your points, all the points are your bases, and you're kind of reorganizing them in a diffeomorphic way to see R alpha instead of F. It's a change of. That's it. So I want to solve this equation.
Maybe there's some like difference between like mathematics physics notations, but when you write like H of R alpha, there is like some kind of
This is H composed with R alpha. So
there's no commutation.
no, there is no commutation. It's here. My equation is H composed with R alpha plus delta F equal R alpha. This is composition here. This is composition. Sorry. Yeah, we have to be precise. Yeah. So what is the main ingredient in the proof? Is that this equation has a solution provided alpha is Jotunheim. Yes, and the analysis of the equation is extremely easy. If you decompose your f along Fourier modes, you get that hk, the Fourier mode, must be equal to delta fk divided by 1 minus e I 2 pi k alpha. And here you see exactly where this condition appears, because it tells you that this small divisor. So here I introduce my first very important word in KM theory, small divisor. This small divisor here has to be lower bounded by something. If you lower bounded by something polynomial, 1 over polynomial, it means hk will be, so small divisor control, which is 1 minus ei 2 pi k alpha, bigger than 1 over k to the power tau. This is the Jotunheim property. Yes, this implies that hk is less than delta fk times k to the power tau divided by gamma. And it tells you that if delta f is smooth, h is smooth. And we're super happy. We're super happy because we solved the linearized equation. But why are we sad? Who can tell me? Why are we not super, like, that's it, we go home, and why did we need Kolmogorov? Because, yes?
Because the estimates on each are in a CR norm, which is higher than the one we have for the back.
Yeah. In fact, lower.
Yeah.
Yeah. So you control h with the loss of derivatives. This is how many derivatives you lose. Tau. Tau, or in fact, if you're not super strong, like if you're not Foucault or something, you will say, yeah, I lose tau plus 2. But then you can start to be stingy here and see. I mean, you lose at least tau. However, you lost tau derivatives, but you didn't become like epsilon over 2 closed. You became epsilon squared. And that's where the whole trick is. And when I said this is more Arnold, it's not Arnold, this is Arnold Moser. Because Arnold did this in analytic. And in analytic, using the polynomial here is even less bad, because on analytic scale, this is small like exponential minus k times delta, where this is the analytic band of delta f. And this guy will be less than exponential minus k delta times k to the power something, which is almost less than exponential minus k times delta. So in the analytic case, you are really close to being able to solve it in with the Banach normal inversion principle, but not really, because you do lose a little bit of your band. And that's what Arnold did. He accepted to lose a little bit of your band, like you lose 1 over 10 to the power k, to the power n at step n of your iteration, and you continue. Now, I want to come to my second very important thing in KM theory, is about transversality. It's about being able to keep the arithmetic property alive during the iteration scheme. If I was doing this, I would solve this, that in fact I like, because there is the Fourier coefficient at 0 that I cannot solve. We know that this can be solved, provided this. Okay? But now this integral is 0. And that's why I can solve. If not, I will be able to solve not this, but this for another guy. And this new guy, I can try to work with him next time. But he's maybe now not Jotunheim anymore. And therefore, you can either fix the rotation number through a condition of this kind, or consider parametric families that give you the transversality you like. And that's more like the physical way of doing it. If you want to do it, you would say, let me take R alpha plus T plus epsilon delta F, or let's take RT, and I call this FT. And now what Arnold tells you that T in 0, 1, such that FT is C omega conjugate 2 R of some angle that depends on T, and this angle will be close to T, but not necessarily T, of course, has almost full measure, provided epsilon is small. And the more you want your measure to be close to 1, the more you will take epsilon small. Okay? And what is the trick here? The trick is you start with RT and you linearize like this. However, you get a new T, a T prime. Okay? And you say, which are the T for which I can do step 1? They are the T that are Diophantine. And Diophantine with some constant gamma here that depends on epsilon. Like you can take gamma square root of epsilon, say, right? Because you can divide epsilon by square root of epsilon and you are still square root of epsilon. You're happy. This will give you the fact that you are looking for a constant gamma here for the square root of epsilon gives you a counter set of almost full measure, like 1 minus square root of epsilon. That work for step 1. But then you look in this counter set and you say they gave rise to a T prime. And this T prime maybe is not good. However, the T prime, you're now comparing it to a smallness of order epsilon squared. So you can accept that T prime be Diophantine, but with a constant gamma that is less stringent. Okay?
Can you restate the Diophantine conditions?
This is the Diophantine condition.
Yeah, can you say that means?
Yes, you're right. Sorry. If you take a guy in the street, you tell him, tell me what's an irrational alpha. You have a good chance that you know. But we in mathematics cannot stop there. We need to know a little bit more about the irrationals. There are the good irrationals and the bad ones. The good irrationals are the irrationals that are really irrational. They are far away from the rationals. Far away from the rational is like in dimension 1. Huh? Let's do this for d equal to 1. It's alpha. Yeah. So let's do d equal to 1. So alpha, not in Q, is dc tau gamma if alpha minus p over q is bigger than gamma divided by k by q to the power 2 plus tau. The 2 here is what directly tells you cannot be bigger than 1 over q. You will always have a guy who approaches you more than 1 over q squared. However, you can be good in the sense like you cannot approach me more than 1 over q cubed. You want to approach me more, you need to pay a denominator. Okay? That is a Diophantine guy. A Liouville guy is like, for example, you take a sum of 1 over e to the e q over q in z in n. This guy will be like Liouville. Yeah? Because alpha minus p over q for a sequence of q will approach here you will get like less than 1 over exponential qn for a sequence of n. I'm saying if you have a number alpha, such that alpha minus Pn over Qn less than 1 over e to the Qn, this is a UV gap.
Alpha here is what's going to become the ratio of frequencies when you do.
Yes.
Why is that? Why is alpha like ratio?
Okay. No. Let's focus on the circle. I am on the circle and I only have a rotation. So my map is theta max to theta plus alpha modulo 1. Okay? If alpha is irrational, I want to conjugate my circle isomorphism to R alpha. This forces me to look at this cohomological equation. And I observe that it is going to have a solution provided the small divisors related to alpha are under control. When I can solve this equation, I can conjugate my f closer to being a rotation. However, there is a constant part in delta f that I cannot keep. And this constant part in delta f will provoke a change in my rotation number. Just imagine you have a rotation angle alpha and you perturb it by an epsilon perturbation that is just, you take alpha plus epsilon. If you take alpha plus epsilon, maybe alpha plus epsilon is irrational. Then, if you start with a rational rotation and you add a nonlinearity delta f, you will blow up the whole thing. You cannot expect any rigidity, right? Because you know that when you perturb identity, it's not going to be conjugated to identity. That's it. Okay? And there is irrational guys that for some iteration, they will look really a lot like a rational guy. And for these people, you will be able to perturb in a way that similar to the perturbation of identity, you stop being conjugated to the linear model. So we can complement this by saying that alpha UV, so this is not DC. UV is the opposite. L is equal to DC complementary. There is another theorem, so this is theorem 1. Theorem 2, Arnold, Arnold, Hermann, etc. Alpha UV, there exists as equal like this. That is not smoothly conjugate to R alpha. So let me summarize. Under 4 conditions, I can recover my linear model. What are the 4 conditions? Regularity, smallness, Diophantine property, and being able to target the Diophantine property I'm aiming at. Okay? It's not enough to start with Diophantine property. You need to be able to guarantee that after perturbation, you continue to see the Diophantine property. So, transversality, regularity, smallness, and Diophantine. Okay. So I promised to say for every item, something old and something new. This is the old. What is new? What is new in this item here is efforts, modern efforts that were done by many people to study more general matrices, not just identity. And not just actions on the torus. So, for example, let's take let's say on the torus, take a matrix. If A is not identity, then everybody knows that there is no kind of rigidity possible. Yes, that you take a hyperbolic matrix, you perturb it, you're gonna be Holder conjugate to it, but you will never be C-infinity conjugate to it unless you ask for many things. So what you can do is you can consider bigger group actions, like ZK actions. For example, you take two matrices, A and B, in SLN Z, and you take two matrices that commute. And you perturb them. Okay? And then you want to know what happened. So KM theory can tell you is working now towards classifying completely the rigidity of affine abelian actions on the torus. When can I say that a pair of matrices can or cannot be perturbed into a pair of diffeomorphisms that commute and that are not conjugated to it? Okay, here we saw I cannot perturb a rotation in a volume preserving fashion while continuing to see its average displacement without being conjugated to it. I call this, I cannot perturb a Diophantine rotation. A Diophantine rotation is rigid. Now, I look at commuting pairs of affine maps on the torus, and I say, can I perturb them? Yes or no? So KM theory is working in this field. For example, there is a famous paper by Damjanovic and Katov in the 2000, where they show the following result. You take two Anosov maps, A and B, automorphisms of the torus, that are hyperbolic, okay? And they commute. And you take two nonlinear maps, F and G, that commute, and that are near A and B in CK norm, then they are conjugated to A and B. This is counterpart of this theory for a mode conjugate. Smoothly conjugate. Smoothly conjugate. The Holder conjugacy, you have it for free. And it's a big sport in the field to upgrade this smooth conjugacy into this Holder conjugacy into smooth. The theory here behind is that when you have symmetries, it's much more rigid. It's much harder to perturb. Okay? So that's one of the lessons also that come by KM in this particular context, is that higher rank actions, because you're calling symmetries and forcing symmetries on your system, higher rank linear actions tend to be rigid. You can look, for example, in SLN R mod SLN Z, you take abelian actions there, and Jenny Wang, for example, has a result now that says that if you look at the maximal abelian action therein, in this famous manifold, the space of lattices, then it is C-infinity locally rigid. You cannot perturb it. Okay. One other development in this theory in item 1 is even in the case of hyperbolic maps here. I take a hyperbolic map, I perturb it. But now I suppose that on all the periodic orbits, I keep the Lyapunov multipliers of the linear map. Then I'm C-infinity conjugated to the linear map. That is what they call periodic data rigidity. You can address periodic data rigidity of anodes of automorphisms in the local regime when you are near the anode in CK norm by KN field. Let me give you one other result that I like a lot, and one field of research, one direction of research that will talk to physics. Let's take two translations of the torus, of angle alpha and angle beta. Like I take this one, and I take that one. Okay? I have two maps, R alpha, R beta. I perturb them in F and G, and I don't suppose here any commutativity. I just take two nonlinear maps F and G close to R alpha. Then, is it true that typically either F and G are chaotic or F and G are simultaneously conjugated to R alpha R beta? What do you mean F and G are chaotic? We mean that if you take on average all the possible iteration of F and G of size n, the 2 to the power n possible iterations, you look what they do to a vector in tangent space, they will expand it. If they do this, you call them uniformly expanding on average. If they are uniformly expanding on average, you know a lot of things about them. For example, they have unique stationary measure, they tend to be ergodic, they will go everywhere as a pair, as a random pair, when you iterate them at random. So that property, uniform expansion on average, is very important. And people believe that you take any two area preserving maps, then they are generically uniformly expanding on average. That these things are hard to do. However, what I say is that locally, you can expect this to be true, at least in parameter. Like if I perturb this into a family FTGT, then dichotomy. For almost every T, either FTGT is uniformly expanding or FTGT is conjugated to R alpha R beta simultaneously by smooth conjugate. Okay, such a result on spheres was proved by Dolgopiat and Krikorian using KM theory. And I claim this is true here also. Okay. Let us start with this item 1 and go to reducibility. Reducibility, I'm not gonna. So I promise not to give proofs, but I have this kind of habit that I like to go into the proof. But at least now erase this proof from your heads, just that for the people who never saw it, this is a small divisor, and this is a Newtonian scheme. This is what is called the fast converging quadratic scheme. Okay, and that is these two ingredients are Km, nothing more. Okay, and now we just
So about this proof, is there like an accessible reference for resistance that also goes into all the details of it?
There are references on this is super convergent, right?
Yeah.
When you say that, okay. I mean, there.
Well, you in Katok's book, for example, Katok Hasselblad book, there is a chapter on the linearization of a holomorphic germ, the Ziegler theorem, and they explain very well the quadratic scheme, and they do it for a circle map. This here they do it for a circle map. It's a small chapter. It's very well done. It really gives you the idea. Okay, let me now go over the other items a little faster because I really want to talk about item 3 because there are physics in there.
Is there so in principle, if I wanted to improve the superconvergent step, are there examples where you have to have even more tighter convergence to beat when you have extra soft divisors? Because with KM, you basically converge, if I remember correctly, 2 orders of like you skip orders.
Yeah, there are various directions. Yeah, in fact, this quadratic convergence shows you that the Diophantine condition is a little bit too much. You don't need as much. So the optimal condition in the one-dimensional case is known. It's the Bruno condition. In this case of T2, for example, we don't know what is in real analytic setting the optimal condition. In the smooth setting, we have the optimal condition, which means if alpha is Diophantine, delta F is smooth and small in CK norm, then conjugacy. But if alpha is UV, we know how to build smooth examples as close as we want from R alpha, in as high as we want norm, the closest. This is called the anodic cutoff constructions or constructions by periodic approximation. We know how to do it. So, yeah, the picture in the single case is quite complete. I mean, there is there's no margin. That's it. In analytic, it's not yet known what is the optimal condition in a higher dimension. Dimension one, it's the Bruno condition.
Yes, sorry, I was just about the question if there was an accessible thing for physicists to look at.
Yeah.
So there is like, in the
Yeah.
now is the Eugene Wave, he has a like short paper with like 30 pages. That's called like an introduction to KM, and it goes through a circle between Montesson and the local integral or near integral.
That I'm not aware of it, but I'm sure he can do something quite good on the topic. So yeah, it would be good.
Who is the author?
Eugene Wayne. He does KM in infinite dimensions. So okay. Now let me just go now. X dot equals A omega T X in RD. Omega is like nothing Q. And you want to, yes,
You mean Q L or something?
I mean what? Omega T.
Don't you want it to be a vector? No.
It can be vector, but here I'm one frequency. My quasi periodicity is around one frequency.
Yeah, but you have a continuous time, so how do you get, you can just reparameterize this image.
You mean, yeah, you're right.
Okay, so that,
What do you mean?
I mean, I want.
No, A.
We have two frequencies that are not interacting, no? So like Q2.
Yeah, you want me to put here like omega 1 T plus omega 2, something like this?
It's okay.
No, it's fine.
But if you only have.
Sorry. My function A is defined on the torus. It's periodic of period 1. However, omega is irrational. So here the function A will not see the period.
Yeah, but that's my, I mean, if A is defined on the torus, then how are you?
No,
A is defined on the torus.
No, it's
A is the matrix, but it depends on time. A is the matrix. A is in GL.
A omega T. You want A to depend on be a function of the torus, no?
I want A to be a function of time. I want A to be quasi-periodic function of time. That's my approach how you define the quasi-periodic function.
No, okay, sorry.
Okay. And I want to conjugate this system to reducible if there exists a conjugacy if there exists P T such that P if I put Y equals say P omega T of X, then Y dot equals some matrix B Y, and B is constant. Okay. So what does KM theory tell you? If omega is Diophantine, if A is close to a constant matrix B, if A depends on some parameter lambda, then for almost every parameter lambda, the system will be reducible. So let me state the general ideological theorem, which is sourced in various classes, but that the philosophy is the following: is that A equals A close to constant to omega Diophantine, and 3A depends on lambda is transversal in lambda. What does it mean, transversal in lambda? It means that the eigenvalues of A, when lambda moves, they all move. And they move in different ways. So for example, if if the eigenvalue sigma 1 is equal to sigma 2, you want that when you move with lambda, they stop being. That's all. Okay. And then under these conditions, then most likely means either for almost every lambda or for a large measured set of lambda. Reduce. So you can see the force of the thing because it's telling you that you give me an ODE with coefficients that depend on time quasi-periodically, and I can solve it. I mean, I can understand it the same way I understand constant ODE, and ODE is constant. This, the major breakthrough that went from large measure to full measure was due to Elias. The start of it was due to Dina Sinai, who applied KM techniques to bring this to the constant by using this quadratic scheme. Which was just conjugating the matrix A quasi-periodically to matrix B. A was close to the constant, you solve the cohomological equation. The cohomological equation involves all the eigenvalues of A. The transversality condition guarantees that whatever small divisor you get because of the resonance between the eigenvalues, you can get rid of it by changing lambda a little. Okay, this kind of thing gives you, for example, in the Schrodinger operator, the particular Schrodinger operator, it gives you the absolutely continuous spectrum Cantor type for small potential and for Diophantine frequency. Yeah. So that's what I wanted to say here. So that's all. What is new? New is that in all you could deal here with multi-dimensional quasi-periodic system like omega 1t plus omega 2t plus omega 3t, where omega 1, omega 2, omega 3 are a vector that is non-resonant if the whole vector is Diophantine. But when omega is one-dimensional, the new techniques allow you to deal with omega irrational without any condition on being Diophantine. So this we call KMUV. And why is it possible? Because in fact, there is a Floquet theory here when omega is rational, unlike what happens for circle different. So for rational guys, you can reduce. It's always reducible. So there is no this input like rational would hurt you. A rational is good. And UV means you look like rational. So when you look like rational, you apply the rational techniques. When you look like Diophantine, you apply the Diophantine techniques. And you bridge out everything and you get it for general alpha. We started this with Raphael Cricolin and Arthur Avila, and now it really is big theory, and it culminated in the works with Avila and on the global theory of these cosine planes. So that's one of the novelties also about KN theory. It's to be able to approach problems that are global when the matrix A is not close to a constant. So you can have reducibility results when the matrix A is not close to constant, but provided the Lyapunov spectrum of the dynamic spectrum is zero. Okay, when there is no exponential growth, then there is smooth convergence. That's the philosophy. That a constant quasi-periodic cocycle either it grows exponentially, it's chaotic, or it is smoothly conjugated to a constant cocycle. Okay. Fine. Let me now go to
this is related to the whole issue about the discrete Schrodinger equation.
yes.
Now, this is important, so for the guy that are more physicists.
For example, if you're studying,
equation, no? There is a discrete version of the Schrodinger equation.
yeah, if you're studying the equation y dot dot minus q of omega t equals E y. This is the question. Then if Q is small, if omega is different time, then the spectrum of this equation, the E's for which that are outside the resolvent, they give rise to an absolutely continuous spectrum of quantum path. This is the most advanced result in the area. Okay, I wanted to talk about item 3, that is the most important point of the theory, I guess. But maybe we finished, I don't know.
Sorry, just to be sure, you have to multiply Q by Y.
I thought, yes. But
Yeah, yes, it's here that we think multiplied by y, it's a
Yeah.
potential.
then the one.
Yeah. This is what the monster did.
Yeah, you want to say the integral, I want you to,
Yeah, and I would like to do the questions.
sorry,
The integral systems either would like to share about that.
I wanted to talk here about the K and tori that appear in perturbation of completely integrable system. So I'm gonna be short. But my problem is the pen, in fact. That is. So let me try to write the least possible. I'm going to work in action and the coordinates immediately. So I'm going to work on RD plus TD. And I'm going to consider the Hamiltonian system H of R theta. That is of the form H0 of R. If I take such a Hamiltonian, you know the equations are theta dot equals dH0 over dr, and R dot equals dH over d theta equals 0. Right? So this foliates into circles, and the frequency on each circle is theta plus gradient H0 of R. Okay? And we say that twist, it's when this map here locally different. RD to RD. Yes? I take small ball around R, I see small ball around delta H0 of R. I see all directions. I see all possible frequencies on my tori when I move up. Yes? I call this twist. You can call it Kolmogorov non-degenerate. And then I consider this plus epsilon H of R theta. And then again, I put my favorite conditions. Epsilon is small, H is smooth. And then I conclude that if H smooth, for example, or analytic, epsilon small, then most tori survive. That's the theory. That is what Kolmogorov announced in the 1954 paper. And that was a huge bomb. Why? Because people didn't know. I mean, Poincaré thought he discovered this. Then he gave a counter argument that showed that, in fact, it is not likely to be integrable. And he showed it's not integral after perturbation, because he showed that the rational frequencies, where this is, for example, equal to 0, so it was identity, they break down into fixed points that alternate between elliptic and hyperbolic. I'm in dimension 1 here. And the hyperbolic guys, they create horseshoes, and these horseshoes are highly non-integrable, and they kill integrability in a full domain where they go, where they sit. Yes? So we clearly use measure in the integrable domain. And what Kolmogorov said is, yeah, you lose this here, you have an eye where you lost a lot of stuff. However, most of the other tori, they wiggle a little bit, they get deformed a little bit, but they survive. What does it mean survive? It means there is this T-infinity curve that is invariant and on which the dynamics of the Hamiltonian flow is canonically conjugated, canonically with the conjugacy that preserve the two form, to the torus, to minimal translation of frequency delta H of phi. So here, this means that, in fact, what you prove is that.
It was known already before.
Just a second. It's in fact what he showed is that for R such that gradient H0 of R is in DC gamma tau, this tau and gamma related to epsilon. For example, if this is like square root of epsilon, then these tori, they do survive, which means for every frequency here, omega r, there exists a curve that is C-infinity, a C-infinity torus, TD, that is invariant and on which the dynamics is conjugated to a translation of frequency omega r. And the idea here is that this parameter r is like the parameter T in Arnold family. It is the parameter that guarantees that once you start conjugating torus by torus, the dynamics to the linear one, you lose tori as you continue because some tori, first of all, you cannot start working with everybody. For example, I said when this is 0, you cannot even start. But for all the guys where this is Joventine up to some precision that is related to epsilon, for example, you start with a tori that have, say, square root of epsilon Joventine. Yes? Then you can do a first Km step. So you conjugate on these tori to the linear map. Then you say, I want to continue, but the linear map you get on the new torus got its frequency modified a little. So at the next step, you will lose other tori. If at each step you're losing square root of epsilon, you will be dead. But you don't, because at the second step, the new nonlinearity that you're facing is a Fourier epsilon squared. So you can allow your vector to be less Joventine than the ones you started with. So in fact, if this is R, you start with this, you're working on all these annuli. And on these annuli, you are conjugating like this, okay? Plus epsilon squared. And then you say, now on these annuli, I first of all bring them down to something horizontal, okay? And then I look, are you good? Do you treat me well? Can you let me do my conjugacy, knowing that I am epsilon squared small? Oh, yes, you're fine, you can go. But some of them will tell you, no, you cannot go. However, the guys where you cannot go are now like measured at epsilon squared. So what you need to cancel from these new annuli are smaller annuli. You will cancel this very small one, but this is very small, like it lives at scale epsilon squared. And you continue doing so. And at the end, you end up with a very tiny, with a Cantor set that has measured almost 1, because you lost square root of epsilon, then epsilon is 3 half. I mean, because epsilon to the power 2 to the power n is your, how small is the order. So you really say. That's Kn.
So
That is the Kn.
what did you want to say about entropy? I'm sorry.
Yeah. No, but I want to,
Yeah, so just to capture some intuition for this. So what are the qualitative differences between the integrable system, the third and the first result you described for linear?
Repeat.
What are the qualitative differences between the integrable system result here and the first result you described for many of those stuff?
Okay. The linear flow I started with had, it was nice because it's just a linear flow. However, it was degenerate in the sense that everything is turning at the same speed alpha. So I can perturb and make it become P over Q, and then I lost it. Here, it's every system here is one of these linear systems that I was talking about. And now when I perturb them, every one that is nice, Joffentine, I can work with him. At next step, he is still a translation up to an even smaller error, and I will test him whether I work with him or no, and I will lose more. But what I lose at next step is less. So, in a sense, here I deal with only one torus, and I try to make him survive, and that's why I need additional assumptions about my average translation number after perturbation. Here, I don't ask this. The main difficulty here is that I have two problems. I have the problem of finding conjugacy to a translation, but I also have a problem of finding an invariant torus. Here, the invariant torus was given. I mean, we were working on the torus, and he will not go away. But here, I must find a torus that is invariant, and I must find the conjugacy. And the strength of the technique, and that's huge, is that you look for the conjugacy and the torus in the same time.
Well, vehicles already knew they see it in the curves. Some
What?
vehicles, it was already knew that some curves should exist. So,
he knew that some curves existed in Lipschitz regularity, but no, and I'm not sure. No, he could not know because no, he could not know that a curve would survive before you know that some boundaries do survive. So
no, assuming that boundary survive.
yeah, if the boundary survive, but why would the boundary?
No, I know, like.
I mean, if you are in the n body in the planet,
But I see now for infinity working on the ceiling.
yeah. He knew that some could, but no, because it could be just a boundary. No, he could not guess any curve. No, no, nothing before that. No.
It's not necessarily like when Gary claimed that he knew and then he died of the surgery. Before the surgery, that he knew that something would survive and then went to the surgery and he died.
I don't think so. No, because when Kolmogorov came out with this, people were starting to believe that there will be more Torah. It even surprised the physics. I mean, usually mathematicians run after the physics to tell them what you're doing is correct. We have the proof, believe me. But no, here it was like not like this.
So to expand on that question a little, so here the kind of new systems conjugate to is effectively having the same frequency of the old system.
Yeah.
Here, did you mention something like the frequency changes a little bit?
Yes. Here, in fact, from the beginning, you don't have one frequency. You have frequency map. It's this one.
Yeah.
And it's because the frequency map is rich. We say non-degenerate. It sees all the world. You can make sure that many of the Torah survive.
And the Torah that do survive, do they retain their frequency just like that case?
Well, what does it mean? Because in fact, suppose I perturb this by just like translating upwards by delta, then all they are like this. But in fact, I don't have the right to translate by delta. But what I mean is that the torus, yeah, the new torus goes like this. And when we say he survived, we mean that a torus with frequency omega gives rise to a new torus with this frequency omega. However, if you want to parameterize the torus not by its frequency, but if you want to parameterize each of your tori as what is the height of zero, right? Zero, angle theta equal to zero, I want to see C of zero or R of zero, right? The height of the torus at zero. Well, in this sense, the torus of frequency omega Diophantine that was at height R of omega will not stay at height R of omega. It will be somewhere, this one, for example, this R of omega is lower than omega. Okay, I just wanted to say that the most advanced version and optimal one about this theorem here is to say that if H0 is just a non-planar function without being local diffeomorphism, it's enough. A non-planar function is a function that do not live in a plane. It's a smooth function that do not live in a hyperplane.
General position.
Yeah, Clarity condition, something like you take the gradient and you take higher order derivatives, you take billions of them, and you show that they span all of R. In this case, you get same result with less precision. You don't know exactly. Yeah, I mean here you know every omega Diophantine survives, right? But when the function is just non-planar, there is the main technical tool is to say that a non-planar function that is smooth hits the Diophantine seriously, like most of the points of the curve will be Diophantine. Okay, that's what you use, but you don't know which Diophantine, which is normal. I mean, if this gradient goes somewhere, there is the frequencies will be there. But when the gradient is a local diffeomorphism, then you know where you go. I just want to say how you apply this to the n-body problem. So the n-body problem was announced by Arnold that he uses the Kolmogorov technique to show. Be careful, I didn't say we live on a quasi-periodic torus or we have a high likelihood of being on a quasi-periodic torus. Not at all. Nobody ever claimed this. Nobody. We are very far from knowing where we live. However, what they claim is that in the n-body problem, there exists an open set of initial conditions inside which Kn phenomenon is present and has large measure. Relative measure in a small open set that is somewhere in the parameter space. So what is the parameter space of the n-body problem? It's 6n dimensions. So we have 6n parameters. So we have like the semi-major axis. Okay, so what is the n-body? You have n planets. They have small mass compared to the sun. One of the planets is the sun.
You know the n-body problem, the planetary problem. Now the n-body is.
The n-body is the planet.
No, the n-body could have, everybody can have the same mass.
Yeah. Okay. Okay. But it still is like what I'm saying. I mean, I'm in the n-body problem. I'm in a very, very tiny place. And this is the place where I am is the planetary type, which is a very, very particular planetary type, where one body has mass 1, all the others have mass epsilon, and epsilon is like 10 to the power minus 300. So we're not in our case because Jupiter is like 1 over 10,000 or 1,000 something. So it's not okay, but it is still the planetary problem. We have n bodies. There are 3n, 6n parameters. If epsilon, which is the relative mass of the bodies compared to the sun, is very small, we are a perturbation of the Keplerian problem. Keplerian problem, we in the three-dimensional space, you have ellipses They have semi-major axis, they have eccentricity, they have the position on the on the ellipse, the angle. So we have lambda, it's related to semi-major axis. Let's say A. We have A and theta. I'm gonna call them lambda and theta, okay? So lambda and theta. And then we have, so these are 2n. And then we have 4n parameters, psi, eta, z, I don't know, z what, gamma. Okay. Now, these are the related to this and to the angle here. Yes? The area that you have. These are related to eccentricities, position in space. Yeah, like if you are coplanar, then 2n of them are like 0. And these are called the secular parameters. Why? Because they move very, very slowly. And in fact, your H0 here is just H0 of lambda. So what is your problem now? Your problem is that R and theta are 6n dimensional, and this is just n. So if you wanted to apply Kn theory, you need 3n directions to see, right? But here you see only n. So you are in very, very bad shape. Okay? You are in very bad shape. So you say, but I have my Newton potential, the gravitational attraction between the bodies. It is my enemy because I want to conjugate it and kill it. But in the same time, it's gonna be my friend. Why? Because I'm going to say, here I have this h of lambda, theta, and these variables. Let's call them sigma and phi. Now these are 2n, 2n. Yeah. In fact, these are not phi. I mean, these variables are in r to the power 4n. There is no torus. Only theta is on the circle because it's the angle on the ellipse. So you say, I have this h0 of lambda plus this. This is transversal in lambda. Like when you take the gradient of this, you get diffeomorphism on Rn, which means that, and here you have an epsilon, which means that you can average this system, you can conjugate this system up to epsilon square, and this you lose.
What do you mean average?
Average means you apply one conjugacy in which you see small denominators like the ones we see before, but, well, you're right. You fix lambda to be some Diophantine vector. Like you fix lambda such that the gradient of H0 of lambda is Diophantine. And you know there are many, most of them. Yes? For such a lambda, you can do a conjugacy that eliminates the theta parameter. Why? Because theta is symplectic conjugate to lambda. And when you try to eliminate theta, the small divisors you see are of the type K scalar gradient H0 of lambda. And you control the small, well, you need to know how Km works. So you apply, say, item 3. You get rid of theta up to epsilon squared. But in any way, this epsilon squared, you forget him for the moment. Because what you want to do is a Km scheme that conjugates you to an epsilon square perturbation, and from there go to epsilon 4, etc. Now you look at this term.
And you say, but how I cannot do much because these terms are like death. They are here, but I know nothing about it. And then you say, but if my n-body problem, if I started with circular, perfect circular, so eccentricity 0, and if I started, say, planar, no, if I started with circular, then by symmetry, there exists a minimum in these parameters at 0. Okay, it's a minimum, which means that this Hamiltonian here writes down as if it was around the minimum, it writes down like this. It writes down as H0 of lambda plus epsilon omega of lambda scalar p squared plus q squared I. Well, no, I hear this is a vector, like, yeah, a vector. And this vector here is 2n dimensional. And this is, of course, P 2n, Q 2n, 4n. So this says that when you look at the minimum of a Hamiltonian, it has this form. Right? It's a minimum of function. It has this form. And therefore, when you look dynamically, you find that the tori here of this system of frequency lambda, this torus, is attached to an elliptic fixed point in the 4n variables, for which this is really a rotation. There is no twist. Be careful, no twist. It's not good for Km. It's just an elliptic rotation. Okay. Now, how did Hermann manage to correct Arnold's proof and make it very rigorous? I mean, the idea of using the nonlinearity to bring in new twist was in Arnold. It's not like he didn't see it. But the proof was not complete because he missed some resonances. He thought that these parameters, this n that you get, he thought you see more.
In the coplanar case, they were working well. But you did one sigma.
Yeah. No, in the coplanar case, you have two n variables that remain. In the coplanar case, you deal with half of that.
Yeah.
Correctly, but there remain one half that is still not nice. You still have to treat it. So anyway, what you see here is this form plus epsilon squared. And now the nice Kn theorem that you want to apply, which is an extension of item 3 that I promised to state, is the following, is that if this gamma omega lambda as a function in R3n, if this thing here is non-planar, there is an epsilon, right? Yeah. If this is non-planar, then this system has a positive measure set of Kn tori that surround this torus times a point. Torus times a point has no, it's not of maximal dimension, but the tori you will get are like this circle times this tangential circle. So this is a 3n dimensional torus that you get. So caveat, I said 3n, I lied, it's 3n minus 1 because there is a bunch of symmetries that clearly, you like rotating the whole planet in space will not change your frequency of the torus. So you cannot be non-planar. You are planar. There is one dimension you lose. So the tori you get are 3n minus 1 dimension. One thing you tell me, but I need to prove this for the planar, for the n-body problem, and that's not easy. So Hermann used to call these things bonjour les calculs.
hello calculus.
Well, if you-
Whenever he gave a talk about this topic, what I remember is bonjour calculus, like hello calculus, good morning calculus. And then there were slides and slides and slides and nobody would follow. But in reality, the idea is very simple. Is what you get is not just this Km phenomenon near eccentricity zero and circle, like we said. You have an additional restriction on the domain where you're working to be able to say that this is non-planar. And this additional restriction is called the well-separated regime, which is the masses must decay very fast from one body to the other. Or if you don't like to move the masses, because people say, I cannot change the mass of planet. So what they do, they say, I'm gonna suppose that the major axis here, it's well separated. Like this guy is 10 billion times greater than this guy, and the one who comes is Lupa, and then Lupa. That's what they do. That's what they find, and this is also like 10 to the power 300, bigger, etc. So we're very far from anything that we know. Why it's useful to put this well-separated regime? Because the non-planarity of this function, you do it inductively by treating first like body one, body two, and then you see that each time you add one more body, it's perturbative because he's so far. Okay.
So, but coming back to the scheme, so to repeat, in the Kolmogorov,
Yeah, I wanted to say a point to answer the question. So there is a more recent proof of the n-body, of the planetary Km phenomenon in the same regime, the same place, but a little bit different conceptually, and that gives you a little bit more by Kerkia and Pinzari. Let's say, and that's important for us to know how to go around the absence of twist. When the system, the integrable system is degenerate, we need to use the nonlinearity to bring in twist. One way is to see an elliptic point and have its frequency move in terms of the fast actions. Another way is to push. So here I had higher order terms, O3 of PQ, right? Because this is around the elliptic point, but it's not an elliptic rotation. The term H bar, this average term, is not an exact rotation. I look at the minimum and I linearize the system to see rotation up to higher order terms. These higher order terms here, PQ, when I'm doing Km here to make the tori survive, I will take them of order, say, square root of epsilon, so that they count like epsilon 3/2, and I plug them in the error. But I can, instead of throwing them under the carpet, like when you clean your house in a sloppy way, I can go and look at them and try to use them. How? By computing what they exactly are. And here I get a second order description, like when you make a Taylor series of function around the minimum. So you get a matrix A of lambda times P squared plus Q squared squared. What do I mean by this? It's just the transpose of P squared plus Q squared vector times A times P squared plus Q squared. It's the bilinear form, the quadratic form around the minimum. Yes? If now this matrix A of lambda is non-degenerate, there's an epsilon. If this matrix A of lambda is non-degenerate, then I look at A of lambda, comma, gradient H0 of lambda, and this is my gradient of my new integrable part. This is like now my integrable part. And this guy here, comma, this is a big matrix in now 6n in 3n dimensions, because this is a 2n times 2n matrix. This is an n times n. And that's it.
graded, it's the matrix of, it's the second derivative of this guy that gives me the twist, right? When I want to see if this guy is planar or non-planar, is it a local diffuse? I take its second derivative, so it's a matrix. This matrix is n times n. This matrix is 2n times 2n. I put them together. If this matrix is invertible, then I have twist. So that's what they showed. They showed that this matrix here has determinant non-zero. How do they prove it? By induction on the number of bodies, and they want to take them very far one from the other to make the induction possible.
But the far away is not the same,
Yeah, far away. I don't know. That's maybe less far away. I didn't go in detail. I'm not super expert in this, but that's the way you look. Okay, you will tell me, but how can you improve this epsilon at 10 to the power minus 300? What people sometimes do, they say, okay, I have an epsilon, it's not 10 to the power minus 300, but I sit somewhere here where I have a Diophantine condition. Yes, so I can do averaging, like some conjugacies. Maybe I cannot go forever, but I can start. And when you start, you transform this epsilon into epsilon square, and then epsilon 3 and epsilon 4. And then you compare, and then you apply Km. So sometimes you can get a little bit better than the straightforward application. And in principle, if we become super good, all these things, we can give them to a computer. He can compute the what we call the Birkhoff normal form up to some order, and then he has the polynomial that corresponds to the integral part that you get after averaging finite number of times. And he checks the twist condition on it. He just takes the second derivative and finds the matrix and says it's invertible, and that's it. So you could maybe find some better applicability. I want to say diffusion. Diffusion is telling you that, well, effective stability is telling you that if you go back to this model H0 of R plus epsilon, this. So Nekhoroshev theory, just if you never heard of it, you want to know that you know it, it tells you that if this function is generic, like open dense somehow, yeah, it has some property that we call steepness, then any initial condition will not move in the action direction, in the R direction. It will not diffuse more than 2 times epsilon before time exponential 1 over epsilon to the power 1 over. So it's called exponential stability, which means that if you start at height R to go to 2R or even R plus 1, in fact, to go to R plus 1, you need exponential 1 over epsilon time. Okay. Then you tell me that you just told us that most tori survive, so I don't move at all during all time. But that's not true, because Km theory tells you there is a positive measured set of invariant tori, but there are holes inside. And in these holes, God knows what's going on. And Poincaré, who's not very far from being having the attributes, I mean, they in mathematics at least, told you that there are horseshoes. There is chaos. And what people managed to do is to put together these chaotic motion plus the invariant tori and show that you can find orbits that do transit in between the tori. They find their way and they diffuse. So it is believed that diffusion is coexist with Km. That the general picture that people believe in is that for a typical perturbation, there will be an almost full measure set of invariant quasi-periodic motion, but that in between these quasi-periodic motion, there will exist orbits that satisfy the Boltzmann aerobic hypothesis. Okay, that there will be orbits that go and visit all the energy surface and equidistribute somehow. I mean, there are various
levels of diffusion we can look at. This has known a lot of progress in C infinity category for C infinity perturbation here, because of course, when you try to do diffusion, the less H is regular, the more you can produce instabilities. The more H is regular, the less you have instability. So for example, when H is analytic, nothing is known about diffusion except that you can build examples where you produce diffusion. But just examples.
I have a question about.
Entropy is the question about what happens to you in the chaotic region outside of the K and tori. There exists a positive magnitude, right? It's not so clear, in fact, because these K and tori that separate leave a positive measure set outside. I showed you here, due to the horseshoes, for example. However, there exist elliptic fixed points, periodic points, that come with their own picture of invariant circles around them. Because this picture I showed you for an integrable system, you can see it around any elliptic fixed point. For a symplectic knot. It is surrounded by invariant quasi-periodic islands. And maybe the picture repeats itself. When you zoom in, you will really see in between these circles that surround the elliptic periodic orbits, you will see the same picture. That's one of the most beautiful and important pictures in dynamics, and I think it has a lot to communicate to physicists. This self-similarity of the phenomena when you zoom in. That's very, very, as a paradigm, it's very important. Now, maybe superposing all these ellipses and of all the generations, maybe you get full measure set, right? Like the horseshoes, they only fill a set of measures. For example, Kierkegaard showed that in dimension 1, if you perturb an area preserving annulus map that is twist, the invariant quasi-periodic motion of order 1 and 2, they fill measure 1 minus exponential minus 1 over epsilon. So the remaining volume on which you don't know that the dynamics is quasi-periodic is exponentially small. That's why it's very hard to tell whether numerically, whether these systems have entropy or not, because you are questioning the question of entropy on a set that is already of measure exponentially small. And the question of entropy is also questioning on that is exponentially hard to decide, because by definition, it's the exponential divergence of orbits. So that makes it very hard. There is a result by Pierre Berger that you can, by very artificial perturbations of an integrable system, create a small island inside of which you have entropy, positive metric entropy. But this is not at all what you get from a typical perturbation. He builds it on purpose in C infinity Berger Touraev to plug in somehow very artificially inside the phase space of the perturbed pendulum. This is the perturbed pendulum, by the way. Somebody asked before, where is the pendulum in all this conversation? This is the pendulum. He finds a very special perturbation of the pendulum that introduces a small disk that is invariant, and inside which the dynamics has positive metric entropy. Yeah, the positive metric entropy is possible.
A couple of questions. One is,
Not analytic.
if I understood this correctly, then so the case that if you randomly pick a point in the free space, then you are most likely to land on a torus that survives. But there is only a measure zero set that leads to.
Not measure zero, I said. This I created by the Poincaré horseshoes has positive measure, and no tori go in. What goes in are second order tori that are tori that surround elliptic periodic points.
So then if I just randomly pick a point in free space for some perturbation, what would be the relative probability of landing on a torus that survives versus landing on some of these weakened cubes?
1 minus square root x.
Okay.
If you want these tori, what we call a first generation. If you are in dimension 1, and if H satisfies very mild non-degenerate condition, like all the Fourier coefficients of H are not 0, then Kierkegaard tells you that the probability to land on these tori and or on these circles that exist in the elliptic islands is 1 minus exponential epsilon to some power. Minus. So it's very likely that you will see quadriperiodicity.
And so another related question, which is in studies of like many body physics, it's usually believed that in something like the n particle problem, as n goes to infinity, the size of the perturbation needed to like break these tori goes to 0. So like, do you have any
Okay,
thoughts on that?
that's a very good question. We have now a bunch of people in Maryland trying to work on this question and saying the following. Okay, suppose we have n bodies, and we know that in Kn, in Necheroshev, in Kn, there is a big problem, not like the curse of dimension, but it is a problem of dimension, which tells you that because the gamma in the Diophantine approximation depends on the dimension to make sure that you have an almost full measure, you need gamma to be very small and decreases exponentially in dimension. Okay, cut the story short. If I take dimension d, then the smallest of epsilon is exponential in d. Like I need epsilon to be less than epsilon 0 to the power d. So the more I put in bodies, the more epsilon must be small. That is one of the reasons why in the planetary motion, since you multiply the number of planets by 6 to get the dimension, you get epsilons that are ridiculous. So we said, okay, let's suppose now that our bodies, they have a decaying mass. Like here, they have a decaying, a well-separated regime. And suppose I put infinitely many bodies, but with the property that the mass of each successive guy is exponentially decreasing. Can I have an epsilon that works for uniformly in n? So now I have R is n-dimensional. This function couples them, but in a way that when R1 talks to R a million, he talks to him, but with exponential minus a million in front. Yes? Then can I have an epsilon? So this H has special form. Yeah, it decays when it involves bodies that come with a high index. Then can I find an epsilon that does not depend on the number of bodies? That makes Km work, that makes Necheroshev work, that makes anything that you do, you want to do it in a uniform way in the number of bodies, provided the masses of the bodies or the semi-major axis or any other quantity decays. Like, for example, the asteroids. We know there are a huge number of asteroids. We don't want to apply Kn and get an exponential minus n, where n is the number of asteroids. We want something that is related to the mass of the asteroid, not their number. So that is one direction of research. It's difficult. It is related to applying Kn for PDEs, like the nonlinear Schrodinger equation, where the phase space becomes the infinite dimensional and with this kind of decay. So it is a problem that is already, it's not completely new. I mean, we cast it in terms of the planetary problem, but it's still, it does exist.
So, Bassam, so it's somebody knows you put all the asteroids together and you sum the mass. Yeah, how large is it?
I looked in Wikipedia because we wanted to know. It is,
The son of the mother of the other.
yeah, it is, I looked like,
Is the actual on Jupiter now?
it is smaller than Jupiter.
The smaller.
Yeah. But it is not like, it is like, you want the mass to be small compared to the number. You want the total mass to be like this. The total mass was like exponential minus n, where n is the number you have. And even like maybe if the total number is like 1 over n to the power 10. Of course, not 1 over 10 n to the power 10 cubed. It's 1 over n to the power 10 compared to the sun. That's what you want, something like this. You want the total mass compared to the sun.
So it's very small.
Yeah. So we don't know for the moment. Yeah. We have nothing on that.
Good. Okay. Any other question? So let's start thinking. There you go, we have both.
Yeah.
Okay. So what it is not, that's.
Do you know how to get this to work?
Are you going to the sun?
No.
Brian, do you need the overhead
I will stay like others.
or black or white?
No, yeah, I like the vector. The cans. How did you get the train together?
Oh, that's it?
Yeah, I mean, just on the projector.
It's recording right now.
Yes.
Is everyone on Zoom? All right.
What kind of connector do you have?
USB-C?
USB-C, yeah, that's also fine.
HDMI.
HDMI. Nice. Is there power somewhere? I need.
Yeah.
You want the whiteboard as well? Like just in case?
We did, why not?
Oh, yeah, we did like this. I like this.
Ah, fractals.
See the lag, right? Like. This is fine.
Huh. Ah, sorry, there's a cable
Yeah,
ring
these
around.
things need like a spray.
Ah, sorry, there's the cable. There's just don't fall.
Sorry.
All good. I'm just worried about you. Okay.
Okay, I'm confused. Why is it? Why is it?
Mirrored?
Yeah,
Yeah.
why does it do that? But then you can't, does it show it correctly?
No,
I mean, I don't really care. If it's mirrored, doesn't it make the writing illegible?
if you're recording it, then no. If for the Zoom meeting, normally it's fine, but if you're recording it, then no.
Okay.
Is this? This isn't yours, right? This copy.
No, no, there was no. I'll get a new one.
I have to leave at 4:45 to get
Okay.
so, and I have to pick up my kid from school. So
That's important.
just in case.
Yeah.
Yeah. How to say it?
Yeah,
Yeah.
won't be offended in any case.
Yeah, the measure of each of the year. The total one is.
This is like, less than 1 over 2 n squared.
Yeah,
1 over n squared.
yeah, 100.
Yeah, because we were doing that, okay?
Yeah.
Less than 1 over n squared. But this is what? This is the error.
Yeah, the measure of
This error. So this guy is 1 over n.
Yeah.
And this guy here is 1 over n squared.
Yes. But this is only for one action,
It's, and then,
and then if you, can I?
yeah.
Just tell me the, what happens if we prove
The
about.
two is the second. I don't know. Okay.
So now let's consider something like this.
Third hand. So it's actually this one.
It actually, so this becomes A over there.
Yeah.
So then.
That's a bit weird.
Order.
Not showing the.
Yeah. It becomes order of one over there. I'm using this notation. This becomes order of one. In particular, when A equals, let's say, n over 2, this is something like one.
I think, and now I know why.
So when A is n over 2, get 1 over n over 2 is something. So when K equals n over 2, you know, so what does this do?
If he wants the n to be, and the n must be close to zero.
Yeah, but so.
No.
So it's something like this.
No, I-
Let's.
Depends on whether you guys start the program or the fact is plug in the thing.
Then E square. I think
Yeah.
Are you gonna hang around?
Yeah. I originally wanted to drink a cup of coffee with mango, but yeah, like. TV penalty beauty.
But this is.
Yeah, he totally.
He can't. People can take it or not?
What is a good?
I saw that.
When you are camera, you took 2 over n, and when you're next.
Oh, when this, yeah, when this speed is. So 2 over n here. Which is up, it's like this. And the reason it implies a
Which is, this is like 2 over n squared.
Yeah, and the reason it implies a is because when you get to T equals n over 2, this intersection must still be like, immediately constructed, but greater than b. Intersection should be. But so it ends up being 1 over.
Spiking,
And this is what has to do with this national.
Depending on what it is. But I think you, right now you're going
Bigger than 1.
No, I did something before. I'm happy to give you. Maybe not tonight.
No, we've not lost half, we've lost one, but there's a 2 half. Or,
Here, the intersection was 1 over n minus 1 over. Here, the intersection is 1 over n minus 2 over.
yeah,
And then
so
it's 1 over n minus
yeah, so.
1 over 2n.
Yeah,
Which
but
is 1 over 2n.
this
This is 1 over 2n.
this 2 that has to be less than 2 over n. Okay, so it is the one minus two T. So this is the intersection. Intersection. This measuring is one minus two T. Like epsilon more than. Right? So, this goes like this, but at n over two, what will.
Yeah, but if I do like N over four, instead of
Yeah.
N over two, I get still one over N.
Yeah, you still get one.
Yeah, like you said, one over N. One over N.
One over n squared is the last term for.
For the last,
for the n. So at that point, it doesn't matter.
Yeah.
Yeah, so I mean, so I'm saying the notion I was talking about is. Like, it's not a bit.
Everything before N over two was linear. Not.
So linearity is a separate word. Linearity is a.
And before I get to that.
Yeah.
So I do see that what important or since we interacted with for P much less than N over four.
Yeah.
Yeah, this is bigger than one over four. And this is.
But it's still like most of the things is outside.
But this is very different from bigger than one over. One over N squared, I can guarantee you, with the Tauric system. But one over four and Tauric system can never. Minus epsilon is different. I thought minus epsilon you can start talking about some kind of simplicity.
That's what I'm talking about.
Yeah, I understand, but you told me one over N squared.
I was using
That I'm not sure. I mean, there is a difference between minus epsilon and four. Yeah, this four and four for four. From one area and another thing.
Yeah.
Right?
Yeah.
And you're not telling me before. So you cannot, for a guy who sees this, call it simply. It's somewhere.
I'm not sure. And the reason there is in Japan's study, this is a bound. It's a bound, it's
We don't know. I would have to.
We said we would only start in like 10 minutes. Oh, there's somebody got deadline. Deadline. Tell me everything. Here. Yeah. Yeah. I like. There's oh yeah. Hey.
Yeah. Also, when it is, not red, now, wild for now. Yeah. Ilya kind of told me basically, they hired this guy, and I'm gonna. But he gets any stuff, there's something in Georgia Tech, which he said. Ah. I do. Did they ever show the yeah, but the other. So it's.
Maybe not.
Yeah, but, but what he said is that the preference would be non-unified. Yeah. But other well, I didn't do like an exhaustive research, so for me, like the things coming on merge. You, nature. And would really have to be that's what I the second part of what you or yeah. Okay, so Chicago, Brown, yeah, Brown, checking the corporate moving was and then what? Applied math is really for students, people who don't fit enough in the practice. But if you have nothing useful to say about the real. But yeah, we'll see. Did you hear back? No. Oh, I did it like the French film, but I still don't be the experience. I know, but I'm eventually and what you told me is the way the French academic system works is like you have some sort of an informal agreement with the lab that if you're selected, that they would be happy to sponsor you. And so I never knew anything about policies. So he suggested that, like, if you really want, if you care about this, like, you should go around in the summer giving talks and that things. You put a usual, even if it's. Then I mean, there's two way I believe for all of that. It's like for mentoring outsiders. Yeah, two AI people. AI revival. Did you mention a lot? Yeah, but I was very the one about the I just clicked around this website on my own account. I hate it. No, you said it might be useful to get in touch with them before the committee. No. Yeah, super.
Quando adesso si dà vedere come funziona, che dipende dalla qualcosa di variabile. Non puoi dire, ah, dai, sì, dove ha well, this is the bridge to access. También es una versión del bridge to access. The point el problema que era punto de la plaza también.
Just want to make sure this is what it is.
Yeah.
Looks good.
Today you can record me, I don't mind. More polished than yesterday.
Okay, sure. All right, we're on the last speaker. The third and last speaker is Rainer Engelken. He's I think he's a local expert on chaos and random and in recurrent neural networks. And I think he told me there's some very interesting new results which are related to machine learning. So it seems to be like a practical application of chaos theory to actually make machines smarter. So that's I think that's exciting. At the end of the day, we see where our knowledge of chaos theory can actually come into play. But I'm being a little glib. I look forward to hearing what you have to say. Very excited to have Ryan here.
Thanks so much for the kind introduction. Yeah, for those who don't know me, I'm Ryan Engelken. I did my PhD at the Max Planck Institute for Dynamics and Self-Organization in Göttingen. Now I'm postdoc at the Center for Theoretical Neuroscience, more interested in like learning. And yesterday we had a little workshop on a tutorial on spiking networks. That's what I worked on before my PhD. Now I'm more into firing rate networks, and I'll define in a bit what this is about. Yeah, so I'm working at the Theoretical Neuroscience Institute, and we think information in the brain is processed by this coordinated activity of large-scale neural circuits. Here you see a zebra fish brain, and a huge challenge to understand mechanisms by which this complex activity gives rise to functions such that these fishes can process streams of incoming information, perform decisions, and control motor output. In theoretical neuroscience and machine learning, very often we describe that kind of complex dynamics in terms of firing rate networks where individual units have a continuous variable. The individual units are very often extremely idealized, simplified, and complex dynamics arises through the recurrent interaction. And among those complex dynamics can be chaotic dynamics. And so today we'll have a dynamical systems perspective on understanding that better. I think I don't need to tell you that we distinguish very qualitatively different states in dynamical systems, like stable dynamics where small perturbations exponentially decay, and chaotic dynamics where infinitesimal perturbations grow exponentially. And there's the ways to quantify that is calculating the Lyapunov exponents, which give the asymptotic exponential rate of divergence of nearby trajectories. So in general, these Lyapunov exponents depend on your initial condition, in this case H0, and they give you asymptotic properties of the system. There's not only one Lyapunov exponent, but in an n-dimensional system there are n Lyapunov exponents. They are given by the logarithms of the eigenvalues of this Moseledic matrix, which is this inner product of the long-term Jacobian, and the long-term Jacobian is built up of a product of individual Jacobians, which basically at each moment tell how infinitesimal perturbations in the tangent space are evolving in time. So generally, this is a product of non-commuting matrices, which makes it tricky to work with it analytically. And there's which we already heard about earlier, a subtle link between chaotic dynamics and information theory. So chaotic systems over time pull nearby states apart and make them distinguishable, which corresponds to a Kolmogorov-Sinai entropy rate. And it's generally challenging to calculate entropies in high-dimensional systems. However, if you have smooth densities along the unstable manifolds, you can estimate this Kolmogorov-Sinai entropy from the sum of the positive Lyapunov exponents. Caveat is showing that the conditions which guarantee the equality here are fulfilled challenging to show. So you have to show that your system is endowed with an SRB measure, but that's something which very often is just assumed. So today I want to talk about input-driven systems, and for that, perspective of random dynamical systems can be useful. Here the idea is
Can I ask a question
Sure.
about the entropy?
Of course.
So since there were some quantum, things happening earlier.
Yeah.
This T transpose
Mhm.
is a self-adjoint operator.
Yeah.
And the sum of the log of those singular values would be the von Neumann entropy of the state described by that self-adjoint operator. And here you're saying something about the entropy being the sum of the lambdas.
Mhm.
Is there any kind of
So the intuitive understanding of this dynamic entropy rate is maybe if you think of a Baker map, you have certain directions along which, like if you have a dough along which nearby raisins are being spread apart, and all the positive, like expanding directions contribute to this dynamic entropy rate. That's why you have the sum of the positive ones. So basically what this is quantifying is how infinitesimal phase space volumes grow along the unstable directions.
I think the short answer to your question is, it's what you're noticing is some kind of metaphor. I don't see any obvious connection. You want to interpret this T, dagger T, as some kind of density of states, or like a density matrix, and then compute the von Neumann entropy of that, and that's equal to the Kolmogorov-Sinai entropy.
Yeah.
No, it's just the interpretation of what we're doing. I don't know, but
Yeah.
it's true except for the logs.
Yeah.
Yeah, so for random dynamical systems, what we're looking at is a set of different initial conditions, and we want to know how they evolve for a fixed input realization. And so if you have Gaussian white noise drive, there are certain guarantees between this microscopic measures of stability, like Lyapunov exponents, and global system properties. For example, if the largest Lyapunov exponent is negative, it's guaranteed that asymptotically smooth densities will collapse onto a set of measure zeros, or onto a random sink, what's it called. And conversely, if the largest Lyapunov exponent is positive, you have a time-dependent chaotic attractor. And for these noise-driven systems, it's actually easier to show that they fulfill this SRB property, which guarantees that the sum of the positive Lyapunov exponent gives the Kolmogorov-Sinai entropy rate. So here's just a little demonstration. I used a vanilla recurrent network and projected it on the first three principal components. On the left-hand side, I drive it with very weak external input. Each point is now a different initial condition. And here on the left-hand side, these
you have this time-dependent chaotic attractor on the right-hand side. It's driven strongly such that the largest Lyapunov exponent is negative, and then over time, this distribution or this density collapses onto a single time-dependent trajectory, a random sink. Yeah, and that's what is, for example, in neuroscience relevant because we want to understand like when are systems reliable? Yes.
Sorry, why is the random sink? What did you do to make it random?
I mean, it's driven by a frozen noise realization. So driven by a random noise, by noise realization, a frozen noise realization. So you have a set of different initial conditions, and they all inputs now receive, all initial conditions receive over these initial conditions the same identical noise realization, and that makes them collapse over time.
But extremely.
Yes, because it's the same noise for all of them. So by frozen, I mean it's like the same across the. It's kind of like complementary perspective to Fokker-Planck. At Fokker-Planck, usually you have a single initial condition, and then you drive it with noise, and so it spreads out over time. Here we have a set of different initial conditions, and we drive them with identical noise, and then we can like see whether they collapse into a single time-dependent trajectory, or whether you.
Like, we say, I take a dynamic system, I take a ball, and I start iterating this ball. And at each iterate, I move by some randomness, but I move everybody by the same random.
Exactly.
And dynamics is collapsing because it's in sync.
Yeah.
But the randomness moves my sync, and I see that picture.
Yeah.
The random.
Yeah. But here, this is a guarantee also for your ball can be big. It doesn't have to be infinitesimal.
Why? Because lambda negative, you didn't say it's global attractor.
Yeah, it's a microscopic stability, but what can happen is that you collapse into different time-dependent trajectories, but they overall.
It's negative everywhere.
Yes.
Okay.
Ryder, can you say something about the noise? Is it just like a OU process?
I mean, in this case, it's Gaussian white noise. There are all kinds of different versions of this. Basically, successively, people proved it for different kinds of noise and showed different properties. To my knowledge, but there are no results on like that tell you how long you have to wait till you collapse, and that would be something very useful.
So it's just some time-dependent noise, but same parameter.
Yes.
So Lejeune, you mean based on the circle diffeomorphism?
Yes.
With random thing?
Yeah.
Yes.
And so, summary. No, there's a question.
Yes. So Lejeune, what he does, he takes like two diffeomorphism maybe, and he aggregates them randomly. And then you get this phenomenon of random thing. But it's not like it's really the randomness in the iteration, not the superpose. There's no random motion.
And yeah, and wait. So that was the first paper, and I think the second one with Buxton, they built up on the first one where they have Brownian motion. Maybe we can discuss that later. Yeah, so in summary, the sign of the first Lyapunov exponents tells us whether the system is stable or unstable. Under certain mathematical constraints, the sum of the positive Lyapunov exponents give us the entropy rate. And then there is an estimate of the attractor dimensionality coming from the number of Lyapunov exponents that sum to 0. So that's a linear interpolation to sum to 0. The idea is that the positive Lyapunov exponents compensate the negative Lyapunov exponents at this number. So the idea is you start with an infinitesimal ball. It's being stretched along some directions because of chaos. Overall, the system dynamics is dissipative. So an n ball would collapse, but D is now the dimensionality which neither grows nor shrinks, but it's just being deformed over time.
Oh, that's a recap from yesterday. That's a Poincaré section through a toy model of a spiking neural network, but today we want to talk about firing rate networks. So the canonical model for firing for chaos in neural networks is the following: that the rate of change is given by a dissipation term. Yeah. Is there a stick? Oh, now I see it. Great.
I think that's a technical success.
Yeah, I like it. I can go outside to some SUV and break down the antenna. That's even more convenient. So this is given by the dynamics is given by a dissipation term and a recurrent interaction term. Jij is a Gaussian is a coupling matrix. In this case, drawn from a Gaussian IID with mean 0 and variance g squared over n. The normalization with n keeps the spectral radius invariant with system size, and g you can think of as the global synaptic coupling strength. Phi is a sigmoid nonlinearity, for example, hyperbolic tangent, and so this system gives rise to chaos that could provide a substrate for learning. So something like that is being used in reservoir computers, for example.
So what are you? You have the HI. What is HI?
HI, you can think of it as a current variable into a single neuron or a population of neurons.
Okay, so it's evolving like a dissipative system.
Yeah,
so
it dissipates.
Back to zero.
Yes, and then you have recurrent interactions where now this phi is your firing rate of neuron J.
Why tangent hyperbolic? What is this?
I think initially just for mathematical convenience, but actually the phenomenon that you get chaos in these types of networks is very generic and does not really depend strongly on the choice.
You get chaos. How many variables I have?
Well, n. N is the number of neurons.
Big N.
Yes, capital N.
And not by chance that you put the Gaussian square over n because you want the sum to be of order 1.
Yeah, so maybe I can just well, I'll come to that in the next slide. Yeah, Jij is drawn from a Gaussian.
Yeah,
and it's IID, yes.
Yeah, okay.
They're fixed. They are not evolving on time.
No, they don't change over time. Yes, and so what we did in a paper which just came out last week in Physical Review Research is calculate now the full Lyapunov spectrum and these estimates of entropy rate, attractive dimensionality, and see how does it change with time varying input? How does it depend on G? Yes.
I was in the PhD session.
Yeah.
Can you provide some intuition for like why chaotic dynamics is useful for machine learning?
Yeah, so in the intuition, I think there's not really a very formal understanding of it. But for reservoir computing, the idea is you drive such a chaotic system with time varying input, and it acts like as a function generator, which generates lots, like with the external input, lots of nonlinear combinations. And then what you train is actually only a readout. And if your dynamics is sufficiently rich, you can now kind of generate different functions based on the input. That is a very vague intuition, and it would be great to have a mathematical handle on like what makes the reservoir rich, and how can we quantify the capacity and the expressivity of this reservoir. And I'll come to the machine learning implications of that a little bit later.
Minus HI, because you want to reward yourself. Like when HI becomes big, it means you're getting somewhere. And
yeah, I mean the leak term, like in neuroscience, you would think it's kind of a relaxation dynamics of the individual, the typical relaxation of the individual current, so current decay over time. If you don't have this relaxation term here, then the network would saturate. Everything goes into the saturation of tanh and nothing happens.
Tangent, can you just remind me? Tangent goes from 0 to 1?
Yes, from -1 to 1. But you could do the same with a sigmoid from 0 to 1. Yes.
Can you say something about what you mean by collective fields?
Well, yeah, that's maybe an important distinction to what the systems we talked about yesterday. You can think really of the individual elements here as relaxators. They're very simple, and the complex dynamics only comes from the collective interactions between them. It's not like coupled map lattices where you have, I don't know, a chaotic thing and you couple it to another one and see what happens with the interaction.
So here you get full Lyapunov spectrum of all exponents positive or
No, we'll come to that in a second. Yeah, so what happens is as you crank up G at a critical value G equals 1, the trivial fixed point becomes unstable where all units are at 0 and collective chaos emerges. So in large N, this is a sharp transition going from fixed point to chaos. For finite N, you have all kinds of different transitions that are more challenging to quantify. And yeah, now, yeah, go.
And the G was the variance.
Yeah, G is the variance of the coupling matrix. You can think of it as like the strength of the coupling, typical strength of the coupling. And yeah, so at critical value G of 1, the largest Lyapunov exponent. So here's now the full Lyapunov spectrum. So in this case of 1,000 units, so it's a recurrent network of 1,000 units. And for G bigger than the critical value, we now have a positive fraction of like a finite fraction of positive Lyapunov exponents. And one thing you can directly appreciate here, there's a symmetry, a point symmetry in the Lyapunov spectrum around the negative inverse characteristic timescale. So where does this symmetry come from? I can just give you kind of an argument for that. If you go to a contracting reference frame, make a change of variables, you can get rid of the leak term here. You arrive at this equation of the dynamics. And if you now flip the direction of time, you get an additional minus, which you can pull in front of the coupling matrix. But apart from that, in the contracting reference frame, the dynamics in the forward direction and backward direction are identical. Now, let me remind you that the coupling matrix was Gaussian with mean 0. So statistically speaking, the forward and the backward dynamics is identical. And so, yeah.
So, okay, so you have like symplectic in some way.
Yeah, it's not exactly symplectic. So in a strictly in the symplectic system, you would have like a pairing of Lyapunov exponents. Here it's a statistical thing. Like if for large N, you find that there is a pairing, well, there's an approximate symmetry in the Lyapunov spectrum. So there's always like a corresponding negative one for a positive one, which is basically the backward direction. Yeah.
I want to make sure I understood something you said. You said dynamics are time reversal.
I said you have the same equation in the backward direction in this contracting reference frame. Overall, the system is not time reversal. So if you run it backward in time, the original equation, you basically have a positive sign, not a like your dissipation becomes positive and things saturate. Yeah.
I have a question just about the geometry here. It looks like you have a coupling from J equals I to N. So this means you have capital N neurons and every one is connected to every other one?
Yes, exactly.
Okay.
But you could do the same if you change the variance, like rescale the variance. You could do the same in a sparse network and would find a qualitatively similar result.
Okay, so the more tau is small, the more the relaxation wins, and the more overall the average is negative. So here you put it at -1.
Yeah.
Okay.
Yeah, and so if we now crank up the network size, we find the large. Well, I should say there's a dynamic mean field theory already introduced originally in this work by Andrea Crisanti, and so you can calculate the largest Lyapunov exponent from actually a Schrödinger eigenvalue equation. Yeah.
Going back to that, that's somehow insensitive to Jij, like the structure of Jij.
What?
That result about the point symmetry of the elements.
I mean, in large N, your whole Lyapunov spectrum is not dependent on the realization of JJ.
No, I mean, this, the symmetry, I see it.
No, it's JJ.
Yeah.
They don't depend on J.
Yeah. So I'm not exactly sure.
It's by definition, there is no dependence on.
No, but
I mean, I expect point symmetry for a random Jij, but if I do some kind of trickiness.
No, then of course not. Like, for example, if you train a network and then ask, like, is it still symmetric after learning? It won't be symmetric.
No, because it's a statistical.
And there's another, in this case, which we chose a 10H symmetry, there's always a symmetry in the dynamics itself. You can always flip from like phi of x to minus phi of minus x. And that will give you also after training the same dynamics.
Can you tell us what you mean by it's consistent learn, etc.
Oh yeah, so usually when
I had an equation.
what people do is they now change this parameter Jij in order to generate a certain output. That is the one way of learning.
What is the output of this?
I mean, so far there's no output. Yeah, I'll come to the learning in later. First, we just want to understand the
As a dynamic system, it came.
Yeah.
And when you do the graph of
the Lyapunov spectrum.
exponents,
yeah,
it's including the noise, including the randomness of Jij.
Yes.
Yes. So this is on average.
Well, for a large network, you don't need to average because all the networks have for large N the same Lyapunov spectrum.
Yeah, because if you look at the equation, if she is small, the majority of Jij will be close to 0. And so who is governing is the negative part. And so there you have an track. When the G is large, you have more distribution, and so you're starting to become Jij that is much larger. And then they are going to dominate the attraction part of the linear part.
Okay, but the Lyapunov, when you draw a picture on Lyapunov spectrum,
yeah,
this is for a given realization.
Yeah. So what I show here is the
noise you draw. And you think for the typical noise or on average?
Yes.
That's what you say.
Yes. So what I plotted here is the average over 10 network realizations.
Okay.
But next we go to large networks, and what you then see is that for once your network is big, the fluctuation of the Lyapunov exponents vanish with like network size. Yes.
So what are the conditions you need for that symmetry about zero?
Yeah, the symmetry here comes from the symmetry of the distribution of Jij.
That's all. So
yeah.
Not the nonlinear.
No. But so it wouldn't work, for example, if you use ReLU, you usually also have to include a bias current, and that then you would have to also flip the sign of the bias, so only for like without bias. Yeah, good question. Yeah, there's another question. Oh.
No, I mean, the nonlinear. I mean, if you would have a nonlinearity without the symmetry, it's zero. I mean, you would not see it. I mean, don't you use that you can take the negative sign outside? The pi when you do change your coordinate? No, sorry. No. No.
Yeah, that's right. Yeah. Okay, so we also find that the system shows signs of extensivity. So here you see the largest Lyapunov exponent as a function of n. It saturates pretty quickly, and if you calculate the full Lyapunov spectrum for different network size, they coincide if you rescale the entire spectrum by n. And so that.
The equation. So.
Equation. Yeah.
Yeah, well, yeah. So the field the tangent.
Yeah.
So, well, the tangent goes between -1, 1.
Yeah.
What happens is you do something dramatic, and you use just something linear. So the P is H.
Yeah, in that case, your system dynamics will explode once you have G bigger than 1.
Yeah, but then you cut it. You make something dramatic.
You can do that. That's called like a hard 10H, and then you have kind of like a piecewise linear function, and you change here the slope parameter. It's pretty much the same.
Well, no, but keep the discontinuity. It means that forget about the hurricane, the derivative, no? So.
What?
No. You see that they don't try to smooth.
Yeah. So there's still kink here.
Okay, good. And basically the result is the same,
Yeah, the qualitative dynamics is the same.
because in this case, it's like a linear system that's engaged.
I mean, that you can think of this as a combination of two rectified linear units.
So in one part, so when H really large.
Yeah.
Who govern is the negative part, which is the attractive part. Because of the negative, no, so the right hand side doesn't exist.
Yeah, I mean, what happens is that most units then live in saturation.
The saturation, and so who dominates are the difference between the GHA and one.
Yeah.
Okay. Everything is on.
Yeah, I think there's lots of things in a simplified version of this where you can do analytics. So yeah, well, it seems the Lyapunov spectrum is independent of network size, which trivially implies that entropy, dimensionality, or the estimates of that grow linearly, and that is a fingerprint of extensive dynamics, which is by itself not trivial. I mean, you would expect that in gases, where if you cut your gas into half, the subsystems behave the same. But here it's a globally coupled system. And yeah, I guess it comes from the way you scale your variance. Okay, so what happens to this chaotic attractor now if you drive it with time-varying external input? We now add a Gaussian white noise term to each unit independently. It was shown before that there is a suppression of strength sigma squared, the noise strength. It was shown before that for discrete time systems with sinusoidal input and on-Stern-Uhlenbeck process input, people calculated the largest Lyapunov exponent and found a suppression of chaos. The intuition is that external input drive brings units into saturation, so effectively your spectral radius gets smaller. Now here we calculate the full spectrum and we see entropy. The entropy is also decreasing as a function of external input. And for very strong input, the system is at this random sink. So initial conditions collapse onto a time-varying trajectory.
It's not the same for.
It is identical across different replica of the entire system, but it's different for different units. So you can think of it as like running the same experiment over and over again with the same input realization. And yeah, also the dimensionality is drastically reduced by time-varying input. For strong input, you collapse onto a point, so 0 dimension.
I mean, it's psi I depend on T, doesn't depend on H. That's the thing. It's psi I, can depend on I, but as a vector,
yes,
an n-dimensional vector, it doesn't depend on the state H. It just moves over the H. And
yeah,
the value of HI, you move by psi I of T.
Yes, it is
that's why it's what you call noise.
Yeah, I would call it a frozen input realization. And so, yes.
So is there like so what happens in sigma H? Do you just have to go farther out?
Yeah. What happens is there's kind of a competition between sigma and G and the limit of large G and large sigma. If you fix G over sigma, you can, I'll show that next, you can even calculate the Lyapunov spectrum analytically, because what happens is that the autocorrelation gets very short.
But why do you say random sync while there are positive Lyapunov exponents? They do.
No, I mean, if you drive it strongly, the first Lyapunov exponent goes negative. There's a suppression of chaos. Yeah, that was for no input. No sigma. Sigma equals 0. The noise strength. So the full Lyapunov spectrum I showed before, that was without time-varying input, without the psi. And now with psi, it depends on the noise strength where the largest Lyapunov exponent is. For strong noise, we can push the entire Lyapunov spectrum to negative, and then we observe these random sinks. And that's what we would call the system is controlled by the input. So generally, because of this product of non-commuting matrices, it's difficult to calculate the Lyapunov spectrum analytically. But in some limits, there are at least approximations. So the first fingerprint of that was we found that the Lyapunov spectrum is invariant and a shuffling of the Jacobians. So you can just take a different order of the Jacobians and find the same Lyapunov exponent. And the reason for that is if G is, so the limits where that works is if G is large, and in this case, the autocorrelation of the Jacobians becomes very short. It scales actually, the length of the autocorrelation scales with 1/G. Also for large sigma, that makes also the autocorrelation short. And there are two other cases when G approaches the critical coupling 1 from above, then the autocorrelation of the Jacobians diverges and the variance becomes very small. So you kind of approximately always multiply the same matrix here. And also for discrete time systems, then Jacobians become uncorrelated. And so in these cases, well, yeah, you can calculate the distribution of the entries of the Jacobian, and you can, yeah, they agree well with the analytical estimate. And then there are even explicit expressions for the entire Lyapunov spectrum. So here it's the Wigner semicircle law in the subcritical regime. So you get the Lyapunov spectrum from the inverse of the cumulative density function of that. And that still works approximately even in the chaotic regime, where you can then get the Lyapunov spectra, the largest Lyapunov exponents from dynamic mean field theory. And in this case where the time is discretized, so that would basically mean you discretize it with an Euler scheme and say your dt is 1. Then it's the Lyapunov spectrum is given by this triangular distribution of Charlie Newman.
So what's the rough, like, just in broad strokes, the
Yeah.
approach here? If you have a product of commuting random matrices.
Yeah.
Then you just diagonalize each one and you can compute the FS spectrum that way? Is it enough?
Yeah, so in this case, there's from I think 1990 a paper from Charlie Newman where they calculated eigenvalues of singular values of products of matrices, and you observe that they converge to a triangular distribution. And from this triangular distribution, yeah, you take the logarithm and then you get the entire Lyapunov spectrum. Yeah.
So I just want to make sure I understand the approximation. So in one regime, you have, when G is very large,
Yeah.
the matrices are weakly non-commuting
Mhm.
because they're random. And then the other regime, they're basically all the same.
Mhm.
And that's where you can.
Yeah. I guess you could also do something in between. I mean, I think this is just the beginning. Like if you really want to push it, you could probably calculate more here. But it turns out that the regime where people usually use these kinds of neural networks is for, I don't know, G equals 1.2, where it's weakly chaotic. And there, this approximation still works very well. So I don't know whether there's any use of having better approximation deeply in the chaotic regime.
They're not really, they don't commute. The matrices don't commute. It's just that the product is permutation structure.
Yes.
Those are different.
No, that's true. Yeah. Yeah. So here you see the analytical estimate as a dashed line, and the numerical result, and these limits, they coincide pretty well. Sorry, yeah, there are more questions?
Sorry.
No, go ahead. It's important. We want to make it interactive, so ask.
So
You have to pick up your
can
kids.
you
I don't.
say something more about the large G regime, like why can you get away with this? Is it because they are weakly non-commuting, or is it permutation invariant?
Yeah, so what happens is for large G that the autocorrelation of the so what matters for the Lyapunov exponent is the autocorrelations of phi prime. right? And that is going to the time scale of this autocorrelation is vanishing with, I think, 1 over G. So, but yeah, there's the caveat would maybe be, this only works if you first take the limit of n going to infinity and then taking the limit of g going to infinity. Because for finite n, what happens is basically that all units are in saturation, and then you go to fixed points. So the limits matter, like in the order in which you take the limits matters. Yeah, and now we come to your question here. This is the piecewise linear network. That's exactly that one. So here you can calculate the entire Lyapunov spectrum analytically. So these, yeah, you can even, so for arbitrary, and there's a mean field theory for the largest Lyapunov exponent, and then for the discrete time network, you can get the full spectrum. Sorry, here is the entire Lyapunov spectrum. Here is the maximum Lyapunov exponent, the entropy rate, and the dimensionality. And so what you can see is that both entropy rate and dimensionality actually have a peak as a function of g. And the intuition to understand that is, while the largest Lyapunov exponent keeps on growing, it grows logarithmically with g. The number of positive Lyapunov exponents is decaying faster, such that overall the entropy is then decreasing. The same for the dimensionality. So, I mean, it's not surprised that the dimensionality cannot grow arbitrarily because it's like bounded by n, but it was surprising to me to realize that the entropy is also bounded. So what that means is that for very large g, you basically have a chaotic attractor that is very unstable along certain phase-space directions, but the number of these unstable directions is getting smaller because more and more units are in saturation. Yeah.
Is it counterintuitive that the stronger the noise, I would have imagined the dimensionality should be higher?
Yeah, that is come misunderstanding. The dimensionality here is basically the dimensionality for the same input realization. So what you are thinking of is like, if I drive it with noise, shouldn't there be like a inflation of the cloud of points? But here the perspective is kind of, you have a cloud of points, and you drive all of them with the same input realization. For very strong input, you saturate the individual units, and the system becomes more dissipative. So overall, you have this collapse to a random sink.
Your analytical formula for the Lyapunov spectrum looks good everywhere.
Yeah.
It doesn't seem to break down.
Yeah, here I think it might break down for large n. It might break down for large g if you don't also increase n, because as I said before, you have to take the limits the right way. So basically, if you first send n to infinity, that should not break down. Oh yeah, and so you can also play the same game now for Lyapunov spectra of other networks. So Kamesh and Tankut have some work I want to point out in this direction. So here is now the full Lyapunov spectrum of the networks with LSTM units. These are commonly used in machine learning because here each unit has a memory variable which is shielding away the system dynamics, and you can create additional slow modes. So there's one, they are interacting with different gates. There's one parameter which is the bias term to the forget gate. If you crank that up, you get an accumulation of Lyapunov exponents close to 0. Here, the entire Lyapunov spectrum has now 2n Lyapunov exponents, and you see this accumulation. It means long short-term memory. Long short-term memory.
Long short.
Yes.
Can it just be fit into your framework exactly by a special choice of J?
No, I mean, you should ask these two people here, they are the experts in LSTMs. But what happens in a certain limit, I think they are identical, is that correct? But generally they are not, you cannot just do a change of variables to go from one to the other.
All this contains the noise.
Yeah.
The noise who brings all the exponents to become negative.
So far, there's no noise here. So the way the Lyapunov exponents go to 0 here is that you have slow latent variables. And so at the same time, if you calculate the autocorrelation, we see that as we crank up this forget gate, there's a divergence of timescales of the autocorrelation.
There's one mention from you. So long short, remember saying that
I'm sorry.
so
Why did why didn't it become no point? It's become long-term.
Yeah, I don't know why they call it long short-term memory. It is just a trick of making recurrent networks solve more complex tasks. One aspect of it seems to be that they are more trainable, and I'll come to that in a bit, but there are also additional, I think they're also richer in the dynamics.
So the idea that the short memory happens a long time. So you have a property which is short memory.
Yeah.
And the idea that your short memory.
Yeah, it's spread out. It's spread out over time.
Okay. So every day I have to remember. Doesn't mean that I have long memory.
I think the idea maybe
go for it.
You know, is that if you change the JIJ, that's long-term memory. If you just look at you change the JIJ, change those things, those are synapses, that's long-term memory.
But what do you mean change? Because the idea was you have one dynamic that will fix the JIJ.
Yeah, but I'm saying this is the definition. If you adjust JIJ and then when you do machine learning, you adjust the JIJ.
Okay, so
that's long-term.
Now, okay, so you
short-term memory is just the trajectory.
Okay, let's go.
That's it.
Yeah, let's go over. So you say that you have a dynamical system.
Yeah.
So if your dynamical system is autonomous.
Yeah.
Forget about change.
Okay, fine.
So if your system is autonomous, meaning that the dynamic doesn't change on time. The equation that
yes.
Yeah. This will be
short-term memory.
Short-term memory. And the idea that now you have a dynamic
that depends on some parameters and you have a long-term memory.
Now, yeah, that you have the right to count those parameters.
Yeah.
And this is the long-term memory.
Yes.
Yeah. Okay.
Yeah.
So an autonomous dynamical system is short memory, and non-autonomous, where you have the right to be choosing the parameter, is a long-term memory.
Yeah. One thing about these networks to keep in mind is
No, okay, but
yeah.
You can think about the JIJs here as being modulated by the H. Which is a complicated thing.
The H, it was the function.
H was value.
The value itself, yeah, the coordinates.
Right, so now you have a multiplicative interaction where the JIJs are effectively modulated by the H.
Yeah.
I can give you a concrete example of it, of a short-term memory. Let's say you have a fixed point. Yeah. Your dynamical system has a single fixed point.
Okay, good.
Right? And so that's how is this a memory? Well, you hear a cue or someone singing, and then the dynamical system flows to that fixed point, and then you finish the song. Okay, that's the idea. That's the idea of short-term memory or something like that. That the attractor is there. The attractor itself, that's called the long-term memory. And adding more attractors, if there's some prescription for adding another attractor and another one and another one, that would be adding more long-term memories. The short term is how you based on whatever you see or what you hear, how you flow to one attractor or the other. Something like that.
You had a question.
Well, I think this is a very interesting discussion, but also very surprising to me. I mean, because I thought that the JIJ, just sort of describing how each neuron was connected to another neuron.
Yes, exactly.
Okay, and then I think of LSTM as just being, you can draw a diagram, like in layers with the short-term memory cells and everything. And then I just thought that was a particular way of connecting the neurons. So I thought it could just be reflected by a particular choice of JIJs.
No, that's not true. It's really, it's like that.
Said that that's not.
Yeah, the individual units now have an additional.
Suppose I'm coming to oscillator. I put some function, cosine, theta I minus theta j. Okay, now when they evolve, this cosine will couple them more or less depending on where they are. This is the short term coupling. But if I put a coefficient lambda in front of the cosine, this lambda I can modify it while I'm working. To say, for example, lambda ij is big, but lambda 1, 2 is small. This is maybe like the long term memory of changing parameters of the coupling. But both work in the same way of coupling. It's both are memory, and memory is coupling, right?
Yeah, that's the idea. You had a question.
No.
Not okay. Yeah, let's move on. I have a second part of the talk which I would really like to discuss with Tankut. So, okay, here you ask about input. So here now the dotted lines are input. What happens in this network is you can drive it with very strong input, and external input doesn't have the same effect on chaos in these LSTM networks because of the latent state is shielded from the dynamics. You can drive it with strong input, and still the largest Lyapunov exponent is 0.
What do you say, Ian?
I just said that these LSTM networks respond very differently to time-varying external input, and that is, as Kamesh pointed out, because of this multiplicative interactions between units. So now in the second part, I want to go towards machine learning.
Wait, do you see that the inputs increase? Yes, for LSTM, do you see that?
Yeah, I mean, here is a region where it seems that external input can boost the dynamic entropy rate. Yeah, and generally chaos can be boosted by time-varying input. We discussed that before. Yeah, so the way people train recurrent networks is we have external input, like X drives the network. We have a recurrent network state that depends on its own history, and we have some external output Y of t. And the way these networks are trained to solve temporal tasks is, and we now consider discrete time networks. It's kind of like the vanilla model used in machine learning, where we have a map that describes how the current state depends on the past and some external input. Now the parameters are W and U, and they can be changed throughout learning. The way they are being changed is we unfold the dynamics in time, and now we want to, for example, generate a certain output value depending on the history of the input. So the way you do it is a gradient descent. For that, you have now to evolve the gradients through the recurrent network state. Now, yeah.
So what other variables?
Yeah, now we have a recurrent coupling matrix W. Yes.
You want to study that, you want to calibrate that, you want
yes. We vary the parameters of W, and this will change how the individual units depend on their own history. And we have some input X, and that also has a coupling matrix in front of it.
So the UXD is external.
Yes.
So first you have HTW phi HT minus 1.
Yeah.
Okay, and then the calibration is the U.
Who gives you phi? Who gives you W? Who gives you or are you looking for them?
No, you choose usually your phi. It could be a 10H again, or a rectified linear.
No.
You initialize W and U, usually with some Gaussians.
This W is this JIJ.
Yes, but this time it's discrete time, so I use the machine learning notation.
Okay.
They call it W. Now we're doing machine learning.
And the UXD is XT is not. It's maybe noise and maybe some deterministic stuff.
Yeah, the X is usually some input signal. So you drive your system with an input and you want it to create a certain output later on. And so it could be, for example, what is the weather today, Monday and Tuesday, and I want to know what is the weather today. So I want to analyze temporal data that have temporal structure in them, a sequential data. It could be language.
But it's controlled by some of the dynamic, this XP, how is
That I will give you some concrete examples later, but for now it's not specified yet.
And the XIT, is it XIT part of it?
There's no XIT, there's no noise for now. No noise. Okay, so what I just said is we train that by unrolling it in time. Yes?
Are you adding the training dynamics of W changing?
No,
No.
that would be like the next step. That's another talk.
Okay.
And so what I wanted to say is, if you have some loss function, which is some function of your actual output compared to some target output, you take the derivative of this loss with respect to network parameters, for example, your recurrent weight. If you calculate that, you have to apply a chain rule over and over again. But it depends not only on the current network state, but also on the history, because the recurrent couplings also shape the network state. So you have basically to apply iterative chain rule, and you arrive with terms that involve this long-term Jacobian. So you run into this long-term Jacobian when you ask, like, oh, how do I have to change the coupling matrix here? And you have to basically take the product of Jacobians through this entire network state. And now you can directly see this long-term Jacobian is exactly the mathematical object we ran into doing Lyapunov, calculating Lyapunov exponents. So the two are related to each other.
By itself, just depends on the previous state. If not, like this is just because you're unfolding back.
Yeah.
Function by itself only.
Yes, exactly.
Why you're not changing? Private.
Yes, that's not being changed.
When he asked you whether you fine-tuning W, you said no, but you seem to be doing so because you're taking derivative with respect to W. You want to know how to.
Yeah, now we are learning. So now we change the parameters, both W and the input and output vectors, in order to achieve a certain goal.
Okay. That minimize A.
Yes. Yeah, and so exactly. So now you run into this long-term Jacobian, and that gives rise to a phenomenon called exploding and vanishing gradients. So this tends to be numerically unstable. So bridging long time scales in recurrent networks is challenging because of this numerical instability. And that is why these days, like, transformers are being used instead of recurrent networks.
You mean this may have a positive Japanese?
Yeah, or it's both. Well, I'll come to that in a second. If you have a positive Lyapunov exponents, your gradients explode. If you have a negative Lyapunov exponents, your gradients vanish. So then you can change the input, you can change the parameter here, and you won't find any output, any change on your loss.
So both cases you're not happy.
Yes. Yeah. So you want to have Lyapunov exponents at 0.
Right. You have to go somewhere critically.
Exactly.
But
yes.
If I understand what you're saying correctly, you solved the problem with vanishing and exploding gradients.
Yeah.
Yesterday, you gave us a numerically stable algorithm for computing this.
Wow, you're already 2 steps ahead. So first, I'll quickly tell you, there are different architectures. So how do people avoid exploding vanishing gradients? For example, by these LSTM architectures, or by just clipping the gradient such that the gradient doesn't become too big, or by fine-tuning the initialization. So if you fine-tune your parameter such that your spectral radius is 1, you can use mean field theory in the large network limit, then you can at least make sure that at initialization, this long-term Jacobian is well conditioned. But the caveat is this only works for large N. It has the assumption of IID weights usually, and it works only in the beginning. So once you train, all hell breaks loose. Okay, so here's now the link between Lyapunov exponents and vanishing and exploding gradients. So the long-term Jacobian in backpropagation through time, this is this training procedure that is identical to the forward Lyapunov spectrum. So positive first Lyapunov exponent implies exploding gradient, negative one implies vanishing gradients. We already pointed that out some time ago, and there's a bunch of follow-up, including their work. And but now we want to use that not only as a diagnostic tool, but also to actually improve training. So the suggestion here is we push Lyapunov exponents to 0 to avoid exploding and vanishing gradients. How do we push Lyapunov exponents to 0? Well, the answer to any machine learning question, these days is use gradient descent. So we can use gradient descent to push Lyapunov exponent to 0. But what is the problem? If we write down the gradient expression, now we want to, for example, minimize the square of the first Lyapunov exponent, we run again into this long-term Jacobian. So how can we avoid that? Yes?
That looks like a complicated thing.
Yeah, that's a complicated thing. So how can we avoid the exploding? You have another question? Whatever. You should do it every day. But nobody does it yet. So how can we calculate that gradient? We can use a trick. Exactly what you said. Yes, like Benettin has this scheme of stably calculating Lyapunov exponents in the forward direction. And the only thing which we need to calculate them is the QR decomposition. A way to now do gradient descent on the Lyapunov exponents is basically make QR decomposition differentiable. And there is a stream of work called differentiable linear algebra in the last decade, which gives us the tools to do so. So you can now use automatic differentiation libraries and use automatic differentiation through the QR decomposition.
But it's just to compute the exponent.
Yes.
You don't know how to slow it down. You must introduce some.
So
somewhere to slow it down.
Yeah, he's calculating
well,
gradient.
right now I just calculate the Lyapunov exponents in the forward way. But now, once QR decomposition is differentiable, I can just plug that into a loss function and push them to 0 with automatic differentiation. So yes.
I'm surprised that you can backprop through that, because what happens if two singular values become the same? Wouldn't this QR decomposition not be differentiable at that point? Yeah, so well, maybe I should go forward. So there exists something called an analytical pullback of the QR decomposition, was recently developed. And that gives you now an adjoint expression for your QR decomposition. And you can just plug that into your forward, use that in your algorithm for calculating the Lyapunov exponent, and use it then for gradient descent. So you can now
descent of what?
Of the Lyapunov exponents. Yes. Yes. Well, So first we look on the first Lyapunov exponent. Yes. Well, we have 3 different target values for the Lyapunov exponent of our network now. It's 0, minus 0.5, and minus 1. We initialize the network with a uniform G chosen between 0 and 1. Some of them are very unstable. Some of them are close to chaotic. And over a few training epochs, like less than 100, we can now push our Lyapunov exponent to 0 or to other values. So it works for the first one. And here you see the same now for the.
Sorry, it's a gradient descent only, but absolute value. That's why you put the lambda squared.
Yes.
Because this is like absolute value.
Exactly. Yeah.
Okay.
Yeah. And so now we do exactly the same now on the first K Lyapunov exponents, where K is 32, so we can push all of them to 0, or 16 to them of 0 to 0, or just one of them to 0.
What is your parameter that you're modifying to push to move the Lyapunov exponent?
In this case, W.
W. What is W?
Initially, it's a Gaussian coupling matrix. Yeah.
How many parameters? are you working in
Square, yeah?
n squared? This
Yes.
is too much. How do you do gravity descent on n squared?
I mean, and
Well, it's just the parameters when
I mean, no joke, but that is modern machine learning. Billion
They
parameters,
don't care. They
But you
just
can do it.
optimize on billions of parameters. How?
hundreds. You just do gradient descent, that's all.
So what you do, okay, basically,
Gravity descent doesn't have the curse of dimension.
Apparently not.
Because what the function is.
You do it stochastic. You just pick a few directions. That's fine.
Like, and,
No, you don't pick it, no, you.
It's a totally valid question, but somehow.
okay, let's say you have this big matrix.
Yeah.
You move its coefficient something.
Yeah.
And you look at your function.
Yeah.
And you start tuning your parameters so as to minimize this function. Okay.
so but basically, you are doing the forward, so but you have your W. You want really value chaotic. And so then you are going to be modifying on time your W in a way to guarantee that all the diagonals are going to be zero.
Yeah.
And the way to do it is you do gradient descendant on the coefficient of the matrices.
Yeah. But then you need this function, sum of lambda I squared, to be convex in the coefficients of your matrix.
It is not convex.
Oh, yeah,
It is-
gradient descent is not convex.
And then you do nevertheless gradient descent in dimension n squared and you have the.
Somehow works.
But the subject.
Well, you use neural networks to do the gradient descent set? Or
No.
is it more classic?
Just more classic.
No, just stochastic gradient descent. There's another question.
Stochastic gradient.
Everything you're doing now is just like you're running this gradient descent.
Yeah.
Just to be able to run the gradient descent.
Yeah. So, well, that's a good question. Like, how can that actually be used? So we have two ways of using it. Either you can use it as a pre-training, kind of you start with a random matrix and you just want to make it trainable and then you train your actual network. And the other mode is to do it at the same time. And what we find is, so far we only used some toy tasks, but that's a very trivial toy task. You give it a sequence of random numbers and the network has to spit out the sequence with a delay of d time steps. You can write down the solution by hand, but if you train a normal vanilla network, it would run into exploding vanishing gradients. Yeah.
I have a question which I think you brought up before, which is, why are the gradients with respect to lambda well behaved? Like, should I?
Oh, yeah, something which I forgot to say is, actually, I tried also to push Lyapunov exponents to positive values, and that failed, and I don't know exactly why. So I chose a target value of 1, like positive Lyapunov exponent, and that didn't work. And there are different hypotheses why that might fail. One is the assumption gradient descent is that you can make a small change to your parameters, which has a small change to the loss, and maybe the loss landscape is very rugged. But maybe it's also just the sensitivity to initial conditions that screws up.
I think I can give heuristic answer is.
Yeah.
The quantity of computing is a Jacobi and long one. So the more it is exponentially big, the less you understand what you're going to do. Right? So like when it's becoming zero, you know how to move it. But when it's exponentially big,
Yeah, it's kind of, I have a, like, a question along similar lines,
Yeah.
which is, let's say I do this so that all your exponents are near zero.
Yeah.
Then I would think that a network that was trained to have, this W with that property.
Yeah.
Would be extremely, would behave very unpredictably with respect to its inputs. Because when you put the inputs in, the gradient would be kind of, wouldn't be very close to zero.
So what happens is,
Like it could change with small changes of the input, it could change a lot,
yeah, but heuristically, I can tell you, if you floss all the Lyapunov exponents to zero, what you observe in the network dynamics is that you get quasi-periodic oscillations along many different directions. But I think there is still stuff to discover. And I can tell you later, there can be cases where I think there can be a conflict between what I call gradient flossing, like pushing Lyapunov exponents to 0 and actually solving your task. So if your task is create a stable fixed point, there's an obvious conflict.
And then just following up on the question about differentiating with respect to the lambdas
Yeah.
making sense. It seems like the QR decomposition, like if you have repeated
Yes.
you have eigenvectors with repeated eigenvalues,
Mhm.
then your QR decomposition isn't really uniquely, you don't really have this unique decomposition. So I feel like those would be places where this would not be differentiable. And those might seem like measure 0 situations that you wouldn't run into. But if you think of the training as a path through the moduli space,
Yeah.
then you're gonna have all of these chambers defined by like, one hyperplane where 2 of them are the same.
Yeah,
Another hyperplane where 2, they're gonna meet in lines where 3 are the same.
Yeah, yes.
And there'd be no way to travel very far in this moduli space without crossing through these.
Yeah, but I think what practically helps is you jump over, because you are not continuously training, you're making a finite step. And also, like,
something general, as long as the system is not uniformly applicable, you don't have a uniform cone condition between all the next things, you can perturb them to lower the exponent. It doesn't matter the multiplicity and differentiability of the, it's just that.
I believe, I know, but there is a procedure that you know a priori how to kill all the atoms exponent. Then you prepare your system to kill all them. How he's doing is, a priori you don't have any information on how you do the system. So you have to identify how to do the perturbation or the deformation. This is the funny thing. So he's evolving the dynamics, see all the diagonal, they fall and do it backward.
Yeah.
And then I start to do the corrections in a way to start to do the stuff. So it's kind of do effectively what you want to say. This is the idea is to propose a mechanism that along the base space and evolution where you have to do this modification in a way to destroy the atom component and make it effective. This is the theorem that is what he said.
Yeah, so the machine is finding that there.
Yeah.
Without thinking too much, she just tries, she knows that the definite response must fall because the mechanisms are not uniform. And that's it.
You have this 2-1-1 map, no? On the door, it's like any book that you pick up on chaos dynamics, they talk about the cat map.
Yeah, cat map.
The cat map. And so the theorem that you refer is either you are cat map style or
and small perturbation of its set. When you will apply them, you will not be able to kill the exponent because you have an open cone that is always mapped to itself with an expander. And this you cannot, with a small variation of the parameter, change it. But it seems that what you start with.
However, this is the theorem. So either you're in this cat map situation and it's really bad because it's extremely rigid, or you're in a situation that dilation and curve intermix. And the theorem says that, well, there is a way to do local perturbations.
Like if you have a product of matrices N1, N2, N3, and N, with the Lyapunov exponent that is positive, you insert between N1, N2, and N2, and 3, the same matrix R that is small like epsilon. There is a matrix that you can choose so that the product will have 0.
And so
you know what you can figure out what that is.
Yeah, you can try to, for example, you can cut your matrix into 2 big products.
Yeah.
And then insert in between something that turns the most expanded direction to go to the more contracted. That's not what you want because you want to change the parameter in W. You cannot go in your product change just here without changing. You have to do it everywhere.
So well,
and that's much more complicated. And we don't know how to do it in, say, same thing is happening, this is still more control.
Maybe this algorithm is doing it, yeah.
Maybe the algorithm, yeah, this,
Really, I mean, the learn.
That would be cool.
It's like a family, one parameter family. Yeah. You know, for some measure, it would be. Yeah, by averaging, you know, it's gonna be parameters.
Yeah.
if you apply this, it's like control theory, you apply this to the double pairing.
Yeah.
I have to, how many, they're like, how many you can put at 4?
Yes.
And 3 are unstable.
Yeah.
Can you manage to, when you throw the double panel and start to do basic stuff, can you manage to put it up there?
Yeah, people have managed to stabilize it with gradients.
With gradient descent. This is known that people know how to do it using some control theory, classical stuff.
Yeah.
But with gradient descent, you can stay there.
But I mean, what do you do gradient descent on it then? Do you kick it, or what is the parameter you? So you calculate with gradient descent the right kinds of kicks?
Yeah.
Okay.
So you do the classical.
Yeah, but the inverse.
Yeah.
Inverse stick.
Become the broom, exactly.
Yeah, yeah. I can do it.
Exactly. You know how to do it.
Yeah, this neural network is doing it.
But if you apply this scheme, they're going to find the stability because the system is principally chaotic.
Yes.
And then you apply this, boom, sound is going to be.
Possibly.
Would you find something?
So yeah, it works on trivial like linear examples, also on nonlinear examples. So here, oops, what you see is the test loss as a function of time without gradient flossing. It doesn't train it if the delay is long. With gradient flossing, you can train it. And here, more systematically, we now see that test loss as a function of task difficulty. And if we apply gradient flossing, like the orange line, we can extend the time horizon along which we can do gradient descent. So that's like at least proof of concept that it actually also helps trainability and the difficult tasks. And if you now, to answer your question, if you do gradient descent throughout the training, you can even further improve training. So here's now comparison, either no flossing, pre-flossing, or flossing during training. And you can see that with flossing throughout training, we can solve tasks that wouldn't be possible with flossing just before.
So you're pushing with gradient descent, because like the objective function that you care about is green, and then you push it down to some subspace where you have smaller than this point.
Yeah, so what the scheme what I use here is, first I do gradient flossing for 500 epochs, for 100 epochs, then I train on the task for 100 steps, then 100 steps of gradient flossing, but then after I think 500 steps, I only train on the task. So gradient flossing is you don't have to do it continuously. It's enough to do it in the very beginning. And
I mean, so you do it so you get small exponents.
Yeah.
And then you train it, and then the exponent will stay small.
No. You train it, and the training might change the Lyapunov exponent, but then you do gradient flossing again after a couple of steps.
By the way, the exponent cannot grow up. If they are at 0, they will stay continuously.
Yeah, but once you run it many times, eventually
Yeah, why not?
If you change the integrate the parameter, what happens? Normally, you have a exponent, which is in a central quantity. Yeah. We change just by up. It cannot jump up. So if it works in the good direction, once you make them 0, then it stays here.
Yeah, and so
they become slightly or slightly negative, you react that they will.
So I mentioned before exploding and vanishing gradients, which is only about the norm of the gradient. But here we can actually manipulate also the dimensionality of the gradient. So one way of quantifying the dimensionality of the gradient is calculating the condition number of, for example.
No, I said the exponent is after the same continuum.
So we now calculate the condition number of some map Q of size n times k. So the condition number is given by the ratio of the first n, the nth singular value, which can be expressed approximately in terms of Lyapunov exponents as e to the first minus the m Lyapunov exponent times the time to bridge. So this is now gives us a like Lyapunov based estimate of the condition number, and you see in dashed lines this like theoretical estimate, in full lines the numerical condition number. Of course, this explodes, so it's 10 to the 30. The way to calculate it is you use arbitrary precision integer arithmetics on your computer, like floats or double floats are not enough. And now we see that after gradient flossing, we can push this condition number down. So pushing the Lyapunov, like doing gradient flossing, reduces drastically the condition number. And effectively, this way increases the number of gradients, gradient directions you have. So you can, the way you can see that is here's now the number of tangent space dimensions. And for an acceptable condition number, let's say it's 10 to the 5, now you have like more gradient directions accessible along which you can transport information backward in time. Yes.
I'm kind of curious, right? Like at the end of the day, you're modifying W.
Yeah.
For doing this gradient flossing. Right?
Well, actually, I modified both W, some bias to each neuron, and also the input vectors.
So how different do the Jacobians look at any given time compared to what you'd expect? Like, is it still like circular with the edge somewhere close to 0, or is it doing something drastically different compared to picking a nice initialization?
Yeah, but I mean, one nice initialization would be an orthogonal initialization. Yeah. And if you just look on the eigenvalues of the matrix throughout training, if you floss 75 Lyapunov exponents, you get like a ring, approximately a ring of 75 eigenvalues on the unit circle. Performance-wise, I found that orthogonal initialization is actually worse than Gaussian initialization if you apply gradient flossing. And so my understanding is like for these, sorry, I have to go back, I guess. Well, that's the last slide anyway. For this XOR task, you are basically asking it to combine information from different directions, from different phase-space directions. If you have an orthogonal matrix, they don't talk to each other. So there is like a conflict between gradient flossing and solving your task.
I see, interesting. And have you looked at the W's after gradient flossing with the spectrum?
Yeah, I think I don't have it here, but it depends on your task. So very often, in these delay tasks, you have the number of delay steps of Lyapunov exponents that are close to 0. And then if you regularize your overall network, then you have a strong drop. And do I have it here? Maybe I can just summarize. Well, we have complete Lyapunov spectra. Well, and yeah, in the second part now, we made that link between backcross through time and Lyapunov spectra, and gradient flossing optimizes Lyapunov exponents and improves training. And oh yeah, something I didn't show you, tasks with long time horizons require more small Lyapunov exponents. And that's actually where the whole thing might fail. The QR decomposition scales cubic with n. And so you don't need to do it in every single step. But if you need many Lyapunov exponents close to 0, this is computationally more expensive than doing gradient descent. So the solution to that would be, well, you only need to do gradient flossing in the first few steps to kind of like get a good initialization. And maybe there are approximations to QR decomposition that are numerically favorable. Yeah, that's it.
You didn't say anything about Xi. You said that you were going to talk about Xi.
Xi?
Yeah, Xi is the node. There is no node.
No, I said I talked about Xi in the LSTM networks. There were the dashed lines.
This Lyapunov exponent difference, there is no Xi.
Well, I mean, the task I used was this delay task. So the network is actually driven by a random number in each time step. So you can think of this as a random dynamical system. And I actually do the flossing, including the external input. that means I push Lyapunov exponents close to zero despite the external input. So the network kind of learns to be insensitive to the external input to some extent. And that's also where the conflict between gradient flossing and solving the task could come from. Because to have Lyapunov exponents to zero, you want to have this high dimensional quasi-periodic oscillation. To solve this task, you want to have a nonlinear computation like XOR.
And when you do this, perturbation of the dynamics.
Yeah.
You start with your matrices or whatever system you're talking about. They are always small perturbation.
Yeah, the learning rate is 10 to the minus 3 or something.
So it means that, okay, you have the dynamics. So first you apply this matrix, then this, or this,
Yeah.
and this. And so each time you're doing a little small perturbation.
Yeah.
Not something dramatic. Not something big.
Yeah, actually,
Yeah.
how big are how much do the weights move?
You mean from before to after training? Yeah, I haven't really looked into it. I think there's a lot to be understood here. I feel I have only like proposed this gradient flossing, but now we need to open the black box and see what's actually happening.
Yeah, I think like.
Happy to-
The W would be super.
Yeah.
Super low rank.
Say it again.
So you start with a W zero.
Uh-huh.
At the end of flossing, there's W zero plus delta W.
Okay.
How does delta W, is it low rank?
Well, yeah, no, because the wondering was the following, no? You start, we have a system that, wow, you have to spin and close.
Yeah.
And then, okay, so you can say, I can do the formation where the Japanese component now, you say, yeah, but I change the matrix system, which is cheap.
Yeah.
Put the, so change the dynamic by multiplying by zero.
Yeah. Yeah.
You have a sequence of matrices.
But wait,
Before the heterogeneity, you insert the rotation of angle.
I know, but the question is, if the system is, yes, so,
And there exists such an epsilon that makes the product of zero.
yeah, so this is the question, so I think that in this mechanism, each time that you make a correction, and you found a way to identify this correction, always there are tiny corrections.
I mean, they are tiny in terms of W, but they might completely change your dynamics.
No, I agree, so the long-term dynamics will be dramatically different, but the question is, in each step.
Yeah.
There's
learning.
No, I don't know, because I want to see if the pros, maybe the learning should be like this, I don't know if the procedure is like.
There are two procedures. So first of all, you modify W to make X one zero.
Yeah.
Then you remodify W to make it according to whatever cost L you want to minimize L. It becomes more amenable to tuning L, to minimizing L, because the exponent became new. Then you end up with a new W. Now you make the exponent zero, you relearn, and then you make the exponent zero. And of course, you don't want the exponents to oscillate all the time, but I think that once the exponent is zero, if the change in W to learn and minimize L are not big, the new exponent of the new W will be small.
Sure.
Hmm.
And he showed.
And the more you're modifying less to learn, the more you convert. So it's like a virtual circle.
Well, the question that would be the critical dimension two. Is you have the standard map, or the stat in the standard map, which is this. It's a simple model.
You want to control it, you
Yeah.
make it exponent zero
Yes,
everywhere. What
So,
do you do?
The conjecture and proof is for really large parameter. There are a lot of parameters where the dynamic is ergodic and you have positive outcomes.
Yeah.
But on the other hand, what is proved that there is a residual set of parameters that you are full of elliptic items. There are so many elliptic items, so it cannot be ergodic.
But it's just the house of dimension.
Yeah, I know. But it's a systemic thing.
Yeah.
So the area regime, so it would be intermixing regime where you have ergodicity, because German component region, and maybe they have zero Japan one. Can you use your method to tune the parameter in a way you are having zero Japan component? It's a concrete matrix, it's a 2 by 2 matrices. No, it's a 2
No,
by 2
no,
matrix.
depends, no, it comes in cosine, depends on x. Here he just wants to, it's in.
You put what, okay, so it's a derivada para la lambda.
Yeah.
Why, yeah.
Yeah,
we
we can try later.
Yeah.
Let's try.
It's a 2
Yeah.
by 2 matrices, maybe you can implement in the computer.
But so,
just write them
somehow in these high dimensional systems, it's not a convex loss function, but it's somehow okay.
Yeah.
But maybe for the standard math, you have this very complicated loss function, right? You're saying that you have points where the lambda is.
I'm not
The
sure.
theorem that he said is true, but the question is that you are moving away from the standard map.
Yeah.
You have a standard map, let me finish. You have a standard map, when you do it's really tiny perturbation, a standard map. But the perturbation is not a, is.
You want to disturb the standard, map, not
Yes.
just include the lambda.
No, so I think the theorem is, well, so the theorem says that the standard map, you can perturb it, C1 really small.
Yeah.
In a way that all the diagonals point zero, this is a theorem.
Yeah.
Okay, good.
And you wanna find this.
Well, theoretically, that we know how to find it. And so there are 2 questions.
No,
First,
how-
wait. Ah,
They have, you find you have to build all these rocket towers.
Está bien, pero teóricamente está bien, Juan Pablo. Está bien. Lo que acá empezó la pregunta. So.
We didn't need to know that.
No, yeah, I can know. But it would be, you know, I say that theoretically you know how to do it, but it would be more clear for you. Okay. Good. And so the question is first, can you, your method is going to do effectively this procedure?
Yeah.
And probably, yeah, let's try.
That's right. Yeah.
Let's see.
Yeah.
I will have to see the phenomenon first. Second, improve it. What does it mean to improve it? That maybe when you do this perturbation, it's not only going to be C1 small, but it's going to be CR small. That would be amazing. And much better, it just is enough to do the parameter. So let's go step by step. So maybe it's because it's
Okay, but the first thing is the perturbation that will kill this one depends on X, on it's not like a finite. You need to put it in some neural network where you're gonna modelize it with finite, with these.
No, why do you need a neural network at all? It's, I don't see why you need a neural network.
Because you need to define the map, you need to define the map. And so you have the standard map T.
Yeah.
You want to compose it with a map F that is small. Such that when you migrate, you compose with F anytime, it doesn't go.
Why do you want to parameterize it that way?
And wait a second, okay, look what is this. Is that, wait a second. When you accept that the standard map T has a positive diagonal exponent, it means that after time n, it grows exponentially n. Right? Which means that whenever you want to change something, right, you're gonna go on a exponential minus n scale and have to do something different at this exponential minus n from the other exponential minus n. So it's immediately exponentially difficult to find your map small f. I think so. So how do you find it?
But why do you need to do that after many steps? You could first stabilize it for 2 steps, for 3 steps, for 5 steps, and so on.
Stabilize what?
Like
make the exponent smaller?
You don't have to directly consider the long-term.
No,
You don't know about the expansion.
you cannot do that. In the standard map, because you have huge forces, whatever they call it. And this really trajectory are going to be stabilized when they are falling.
I can give you a heuristic
So
answer.
it's like multiplying.
That is it here.
The one way that everything, so for instance, you have the metric 2, 0, 0, 2.
Mhm.
For many iterations, you are multiplying these metrics. 2, 0, 0, 2, 2, 0, 0, 2. There is no way to stabilize it with one perturbation because basically, but what happened in the phenomenon that suddenly is the ratio, boom, they flip. And when they flip, the relation that it was multiplying by 2 now is going to multiply by the 1/2.
Yeah.
And so there are certain regions, which is the falling part, that they were going to use to stabilize.
But the problem is.
So this is the theory, this is what he was saying. So they have large problems, they're very good, but then boom, flip.
Yeah.
And this is where you stabilize. So you have to be very smart and find measures.
But does the stabilization result like carbon ether?
Say again, sorry?
Does the stabilization result for the carbon ether?
It's like tangencies. It's called is you have what is called tangencies. You have this stable unstable relation, the stable relation. Here is in low, here is in contract, and suddenly the root.
Yeah, but this suddenly here, you may maybe add something that kills the exponent completely for particular x. But what you make here for a different y, maybe.
You have to be different.
So if I have to be different, but how to do it. But then it's here, if you take two math, f and g, that are near the standard math. Okay, and but they are not equal, f is not equal to g, then the random iteration of f and g will be uniformly expanding in the sense that I said before, that any vector on average by these f and g will grow, which means that if your computer is not iterating exactly in that f, but is making a small error each time, you are almost sure that he will always find uniform expansion. He will not be able to create the exponent, as if your system was uniformly hyperbolic. That's what your computer will see. So you don't know what to start. I'm not sure you can start.
So the way people do gradient design is you do a batch. So you don't do that on one trajectory, but you have like 100 or 200 trajectories or like initial conditions, and you operate on all of them at the same time. So would that help your problem?
You have to wait for a long time, as he told you, because if the standard map, if your coupling is very high, you have very strong hyperbolicity, and you have to wait a long time before you go compensated by this.
Yeah, but
okay, long time means that very nearby trajectories have a very different fate.
Yeah.
So you have to treat them differently. So that's it, they're exponentially complicated.
Long time also in a way that you can't control. You don't know how long.
You're trying to reverse the technology. Like we in dynamics spend all of time trying to prove that this exponent is possible. And people say, so yeah, why not? Maybe okay, they fail, it's so hard, it's possible to do something to kill.
No, what he's saying is this phenomena that where you have to fall is going to be dependent on the fault.
Yeah.
But it's okay.
But so if I iterate the map a long time, and I have like the distribution, and I just do batch gradient descent and all these different initial conditions, there's like one point where it's unstable. Couldn't I pick that up?
Yeah, maybe. So because the question, the goal is to go, there is a theorem and there is a conjecture. So the theorem is even one parameter of standard map, any parameter, f, there is a sheet, not a parameter, it's map sheet, closed. So there's a tiny perturbation, that the derivative do flow. Such that for sheet, all the diagonals point C. This is a theorem. How close if f and g are, they are close, C0 close, it means the 2 points by the image of 1 point by the image of f and g are very close. The derivatives are close, but the second derivative are so far away. Okay. So now will be the following question. Can this method find the sheet for given f? Can you do this perturbation in a way that it did give you a sheet that is near by f, such that all the diagonals are 0? maybe she's only see zero flows, only see one flow, doesn't matter. And second, maybe it gives us much more power. But the question is, it doesn't matter how far or the flows in the sheet, but question, even if that the method provide a sheet over there, I know, that is, can you find a sheet nearby in some sense, but such that she have all zero diagonal?
Yeah, let me just connect to this door, because in fact, what you do, I'll kill this one. It's chaotic system, so you cannot have these cyclic towers, like you cannot have periodic dynamics that imitate your dynamic. It's not like you have a box and the dynamics is this box goes here, 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 and then come back. No. But what you can do is you can have, for example, you fix a time big N, and then you can find extremely tiny boxes. Yes, of size E minus N, support, and you take a tower above this tiny box of height N. Then you make another tower of height N, another one height N, and you fill your space, the total space, with these very, very thin dynamically towers, which is a box.
Quick question.
So
What is a tower in this?
It's a disk with its N first in. And we're gonna suppose they are regional.
Tower is your balls with the
That's all. So I take towers, I iterate them n times, and you take it in a certain way to phase your whole total. So this tower one, then I stay there, I take another one, etc. And suppose these guys they fill everything, then you go in the middle of the tower here, and you put a small rotation that it sends this most expanded direction here to the most contracted here.
And you rotate it away.
You rotate it. And this is your F. And this F is small in C0 because it's just rotating this very small box. That's all what you're doing. This is small in C0. And you can do it. And my exponent fell. My exponent now is smaller. However, this map that you put here to have it compactly supported on this very, very tiny board, it's not C1, it's not C2. But maybe you don't care for your neural network, you just put this and then try to teach to do it and drive better, and at the end you find some smooth map.
Yeah, this is for the point of view of these laners, who care about CR group.
Bye.
Bye.
Bye. Thank you.
Yeah, you want just to.
Can I ask you a non-technical?
Yeah, sure.
So initially, when I asked you about the connections and machine learning, you mentioned something like helps to generate like a lot more possible.
Yeah.
But then you spent the second half of the talk trying to get rid of the
Yes. Yeah.
or the disjoint or something.
Yeah, it's two different kinds of neural networks that I'm talking about. So the first part is like reservoir computing, where you have a recurrent network and they are connected to each other and they are driven by your external input signal. And the only thing you actually learn is the output weights. So this generates your desired output. That's reservoir computing. And for that, it's useful to have a chaotic network. For what I talked in the second part is you train all parameters, both input, recurrent weights, and output weights. And to answer your question, here's an example where I did gradient flushing throughout the entire training process. So usually I only did it either before training or in the first 500 steps. But if I continue gradient flushing,
Why is it so weird?
yeah, so what happens, what I do here is every 100 training steps, I do 100 epochs of gradient flushing. The gradient flushing you don't see here. I only show you basically the training epochs. And what you see is whenever I do gradient flushing here, the accuracy drops down to chance level. And at the same time, here you see the norm of the loss with respect to initial conditions. When I do that, it goes big. So gradient flushing every 100 steps helps to make my norm well behaved. But then if I continue gradient flushing forever, I basically, there is a conflict between gradient flushing and solving the task. So it seems, there can be conflicts.
Why is that? I don't quite get it.
Well, I mean,
Sorry, we can take this offline. I guess it's like.
Yeah, who wants to leave can leave. Yeah, I don't shame you. Yeah, well, the accuracy drops down when you push Lyapunov exponents to 0. So there seems to be a conflict between solving a task and having 0 Lyapunov exponents.
Yeah.
And my heuristic intuitive understanding is when you actually do gradient flossing, you generate this high dimension or quasi-periodic orbit, but it seems not to be able to solve the nonlinear XOR task.
For the green curve, when you do the flossing in the beginning.
Yeah, sorry, this is just flossing in the first 500 epochs, and red is now flossing the other all the time, and blue is without any flossing.
So in the green curve, what like when it gets to some decent performance, what does the spectrum look like?
I don't have it here. I can show it to you. I can send you an email with it.
Okay, fine. But I'm slightly surprised that.
It's what I told you before. Like the Lyapunov spectrum for like the here is 0. For a k-step delay task is like all the Lyapunov exponents when this is 0 are like very close to 0, and then they drop down if you regularize strongly. And I think the size of these Lyapunov exponents here is something like maybe e to the minus d, where d is the number of delay steps.
I see. Okay.
But I'm not entirely sure about that. But that's only like an empirical finding.
Okay.
Just a silly question.
Yeah.
You said you couldn't stabilize the method if you wanted to keep part of this from.
Yes.
But in principle, wouldn't that be preferable since you would be able to make faster changes? So presumably faster. I mean, Lyapunov exponent would allow you to move faster.
Well, positive Lyapunov exponents means that now the system is sensitive to initial conditions. So small changes have a drastic effect. You don't have any control in.
Small changes in sufficiently well. You could make a very small change and get very big out.
Yeah.
But you don't have that flow use.
Yes. Yeah. I think that's how people control satellites. They like you because you want to save fuel, you use your rocket and your satellite in the most unstable part of the trajectory because then you have the biggest bang, biggest boost for your bang. But here you don't have that.
Yeah, I think it's the opposite thing because what you lack is precise control over the perturbation during it.
Say again, what
Like what he's saying is, it would be nice if I can control the perturbation so that I get a large change. But if you don't have that control over the perturbation, right? Positive Lyapunov exponents are
not just screw it up.
Yeah.
Right. But so the 0 exponent is the best of both worlds where you can make reasonable size changes while not just blowing up in the other direction.
Yeah, the intuition is you can now you can push error signals across many times along long time line. So here's an example. Here now I show the test accuracy as a function of like flossed Lyapunov exponent, and I find for more complex tasks I need to push more Lyapunov exponents to 0, which might be a bad news because it means that you QR decomposition scales like with n times k squared. So if k is big, it's more costly.
And the number of exponents you put times 0 is the effective space you can move in essentially. I mean,
Yeah, it's the number of gradient directions along which you can send signals down.
Right, because the other ones we just make 0 influence because they're negative and we just nothing happens.
gradients with that.
Yeah. But I mean, yeah, overall, of course, the Lyapunov exponent only control the long-term behavior.
Sure.
And what you care about might also be like what happens to a loop, like to 5-step gradient or 10-step gradient. So we don't really have control of those. Yeah, I get, well, I mean, we can continue discussing. There's lots of things which I don't understand yet, so I can go on.
Maybe we should first thank.
Yeah. Thanks for showing up. That was a fun discussion. Yeah, go ahead.
I just had a question about the thing from the beginning.
Yes.
Where you have like before you put any randomness and before you start the gradient.
Yeah.
Do you have like movable, I don't know, strange factors or something? The initiatic regime, or is it just